I reappear here, and here I collide the last. So that is the billiard dynamics. Okay, so now, so in order to make, so essentially what I was saying that the space is three-dimensional on which the flow acts. And I want to represent the tangent vector because, as I said, the cone that I want to define is in the tangent space. So the phase space in which the motion takes place is the unitary tangent bundle, and the tangent space is the tangent space of the unitary tangent bundle. That is R3. So, fantastic. So, but I want to go back. I don't know if you had this experience. When I studied differential geometry for the first time, I started the course in differential geometry thinking that I knew what a tangent vector is, right? And then the guy started to explain, to talk about tangent vectors, and at the end of the hour, he had given 8 different definitions of what a tangent vector is, and I had no idea what a tangent vector was anymore. So that is a little bit strange, but one of the possible definitions of a tangent vector is just the germ of a curve. Okay, so you just have a curve, and 2 curves represent the same tangent vector if they are tangents, in some sense. Right? Essentially. So I want to use this point of view. So what I shall do, I represent a tangent vector in this way. This is a curve in the configuration space, and then at each point I have a perpendicular vector. So this one essentially tells me the center. I mean, essentially this is a curve, and the tangent vector corresponds to the derivative of this curve, right, at this point. So that is the point at which the curve is based. Then there is the derivative of the curve, which gives me this vector here, which is tangent to the curve, and that is the way in which I move the x position of the because if I have if I make a change of a point here, I can change the position at which this vector is based, and I can change the direction of this vector. Right? So I change where I am in the configuration space, and I change the direction in which I move. So this vector here, tangent to this curve, corresponds to the direction in which I move the space, the point that I'm looking at, while the way this curvature tells me in which way the curvature of this curve tells me in which way the orthogonal vector changes. And so the curvature essentially tells me the way in which I'm changing this vector here, the direction of the velocity, essentially. So this curve is just a way to represent the tangent vector in 3 dimensions. Okay. And I can, it's nice because it has a physical interpretation. It is a ray of part. I mean, if you look at how this evolved, then I mean, things move along. Particles move along this direction, and then you get something like that. Okay. And now I can tell you a base of the tangent space. The base of the tangent space is given by this. So I have a curve like this, which means that I move the point in the direction of the velocity. This is the flow direction, because the base point moves in the direction of the flow. So in this I have Lyapunov exponent that are 0. So this I just throw it away. I don't want to look at it. Then I have a vector that looks like this. The velocity are all parallel, and I move only the base point. And how does a curve like this evolve in time? Well, a curve like this evolves while I travel in time, and I do not collide, it's simply evolved in this manner. And then I have, so this is my two-dimensional representation of vector in the tangent space. I put on one axis, I put this guy, and then I have another guy that looks like this. What does it mean? It means that I do not change the base point, but I change only the velocities. And what happened to this when I move a little bit? It happens this. That this curve ends in this curve. Okay? So here I put this other guy. And now I can tell you what the dynamics does. If I take this quadrant, what happened? It happened that this guy, this vector goes to this vector, but this vector goes to vectors that is a linear combination of these two, because this is a linear combination of this guy and this guy. So it corresponds to some vector here. So it means that this quadrant gets mapped inside itself, but this size goes down. Okay. Now what happens when I have a collision? Let's say that I'm here and I have a collision, right? So I have my vectors are like this, okay? And after the collision, this goes here, and this goes there, and this goes there. So essentially, from the point of view of the cone, is exactly, I mean, the cone is not a one-sided cone, it's like this, right? So, okay, so now I look at what happens to a collision. This is the cone, this is flow, this is collision. So what happens to a collision is that this guy stays put. Because you see, this is exactly, this is minus the other one. It doesn't change anything. The base point remains itself. But this, so this is again exactly this guy here, which the base point does not change, but only the direction changes. So it means that this vector here goes, well, actually it goes down, but it's kind of the same. I mean, so this line goes to this line. Okay. So, okay. What happens instead when I arrive here with a parallel family? Well, if I arrive with a parallel family, then I get something like this. I get divergence. Because this is like, you know, it's a mirror that expands. So I will get a family now that is divergent. So it means that this guy here goes somewhere here. So when I have a collision, again, the first quadrant goes inside the first quadrant, but now this size stays put. And now if I have some flow and a collision, what will happen? Now I have flow, for example. Sorry, convex, but this one is concave. So if you go with a parallel trajectory, it will focus. So if it focuses, it goes outside the cone, right? So you are a little bit puzzled that it looks like it will never work. But in fact, what Bunimovich realized is that, yes, it will focus, but after it focuses, it's expanding, I mean, it's diverging again. And so if you organize things in such a way that it always focuses before hitting again, then you have a situation in which stuff that is diverging, trajectories that are diverging, goes to diverging trajectory. And the condition for this phenomena refocusing is that, oh, this picture is awful. Sorry. Let's do the picture. Let's do a bigger picture. I didn't want to talk about Bunimovich Stadium, but since I started, I don't know. I'm sorry. I tend to drift. Okay. So take two circles. Okay, and then the stadium is this, right? The condition is that these two circles are disjoint. So this is not there. Okay, so this is the stadium, but if these two segments are too short, then these two circles will overlap, and then it will not work. Okay, so that is the, and you can prove it by similar arguments, essentially. So, in some sense, it was a big deal because people did not expect it, but a posteriori, it's kind of obvious, right? It's just that if things focus and you wait enough, then they will defocus the business. Okay. Fine. But now you may be a little bit unhappy about this theorem because you say, yeah, but this control only the maximal Lyapunov exponent. In 2 dimensions is okay because you have only 2 and 1 is trivial. But if you have like a 3-dimensional billiard, for example, what do? I mean, you control the maximum one, but there are, so in 3 dimensions, if the billiard is 3-dimensional, then the phase space is 6-dimensional, but there is the flow direction in which you have 0, then the total energy is conserved, so you have to subtract 2, and then it's 4-dimensional, right? This is 6? 3? Why? 6 minus 2? Why 1? No, you conserve the total energy, and then there is a 1 Lyapunov exponent that is 0. So if it is 3, is 6, minus 2 is 4. Yes. So the phase space is 4-dimensional. So you will have a 2-dimensional, since it is symplectic, you expect to have for each positive vector Lyapunov and a negative Lyapunov. And so you have 2-dimensional, you expect to have 2 positive Lyapunov exponents and 2 negative Lyapunov exponents. And that will be hyperbolicity there. But this guy, Voikoski, tells you how to control 1. What about the other? Okay, so what about the other? In general, I don't know. In the sense that if you give me a general system, I don't know how to control all the Lyapunov exponents. But billiards are special. They are a Hamiltonian system. And Hamiltonian system, they have a symplectic structure. And so if you give me a symplectic flow, then there is another thing always by Voikoski that allow you to do better. So this thing, you can find it in a paper by Voikoski and myself in, I think was 94 or 95, I don't remember. But, okay, so the paper, maybe it was already in a previous paper by Voikoski, I don't remember. In any case, I mean, even if it appeared for the first time, I don't think it appeared for the first time in our paper, but anyhow, it was Voikoski ideas. I have no problem admitting it. So the idea is the point. So let's do the following exactly as before. You have to, let's do it for a map, which maybe is the time 1 map or something like that. So so you have M, but now you have a symplectic form, omega. Okay, so you have so that means that M is 2D dimensional, because symplectic map, they live in even dimension. I mean, you can do something related if you have a contact flow, but okay, let's stick to symplectic maps. And now I want to try to do something that gives me control not just on the top Lyapunov exponent, but on all of them. And the idea is that I want to use this this extra structure that before I didn't have, the symplectic form. Symplectic form is just a 2 form on the space that is non-degenerate, right? So, for example, for the billiard, the symplectic form is simply dp dq. Or dq dp, maybe. Well, it doesn't matter. It's just a minus sign. Okay, so that is the symplectic form for billiard, for example. Okay. Now, there is a problem here that in order to do better, you have to have more structure. And the more structure is a structure that has to do with the cone, because
in 2 dimensions, all the cones are the same, right? They are just wedges. But in higher dimension, a cone, you know, if you cut it, can have all kinds of shapes. And now, how do you? I mean, this is a lot of possibilities, and this seems kind of too much. So the idea is just to take very special cones, which are identified uniquely by simply 2 Lagrangian subspaces. So what is a Lagrangian subspace? A Lagrangian, if I have let L be a subspace in T X M, so this is, and the dimension, and then the dimension of L be D, so half of the possible dimension, and then L is Lagrangian if omega x y is equal to 0 for each x y in L. Okay, so Lagrangian subspaces are just a kernel of the quadratic form. You take 2 vectors in a Lagrangian subspace, you take, so for example, a Lagrangian subspace here, what it is? It is, for example, the vector x, let's say, okay, let me use the notations that I abhor, but physicists like very much. Delta Q 0, okay? This is a d-dimensional space. So these are vectors in the tangent space in which this is whatever, and this is the second component is 0, okay? And now you compute, you take a vector like this, okay? And this, what it is? This is just, by definition, it is this times that. Sorry, I have 2. I need 2, right? So this is 1, and the other one would be delta Q tilde 0. Okay, so these are 2 vectors that belong to this subspace. And now I compute the symplectic form applied to this. It is just this times that minus this times that. So it is just delta Q 0 minus 0 delta Q hat, which is obviously 0, no matter what is delta Q and delta Q tilde. So that is a Lagrangian subspace. Okay, fine. In general, Lagrangian subspace, they have this structure: delta Q, U, delta Q, where this is a symmetric matrix, an n by n symmetric matrix. They are more or less done all like this, but one, which is this one, okay. This is not of this form. It's essentially the only. It's not the only one, but the only time in which you cannot write it like this is that some of this one must be 0. Then. Okay, but you can check that this one is, if you take 2 vectors that are like this, then you get 0. It's a stupid computation. The same computation, like you have 2, well, let's do it. So what it is, this times that minus this times that. Okay, but U is symmetric. So you can take this U, bring it here, and then it's the same and you get 0. Okay. So these are all Lagrangian subspaces. So there are a bazillion of Lagrangian subspaces around. Okay, and what do you do with these Lagrangian subspaces? Well, what do you do with these Lagrangian subspaces is the following. You just say that let L1, L2 be Lagrangian, okay? and then such that and transversal. Transversal means that if you take the sum of them, you produce all the space, right? And so since they are transversal, that means that for each vector v, you can write it as W1 plus W2, where this belongs to L1 and this belongs to L2, because this is d-dimensional, this is d-dimensional, they are transversal, so they form all the space. So this decomposition is unique. There is no ambiguity. And now I define a cone in this way. Oh, sorry. This is a cone. Why is a cone? Because if I multiply the vector by lambda, this gets multiplied by lambda square. And so if it is positive, it's still positive. Because if I multiply this by lambda, this also gets multiplied by lambda. And so this gets multiplied by lambda. This is bilinear form, so you get out lambda square. So this, if it means that the vector, if you have v in the cone, lambda v is still, if you have v in the set, lambda v is still in the set. So that is a cone by definition. Okay, very well. So you see, this is a little bit funny if you think about it, because this cone is some open set in d dimension, but is uniquely defined by two Lagrangian subspaces that are, sorry, this is an open set in 2D dimension, but this is uniquely defined by two Lagrangian subspaces that are in d dimension. So these are d-dimensional objects. So essentially, you have just two d-dimensional objects, and they define uniquely two d-dimensional objects, which is a bit strange, right? It's obvious in 2 dimensions, yes, it's clear. Because in 2 dimensions, you have one dimension, and then you have in the middle, you have the cone. But in higher dimension, well, I cannot do the picture in 4 dimensions, right? But in 4 dimensions, you have, you know, a 2-dimensional space, another 2-dimensional space. There is nothing in the middle. I mean, because in order to make a wedge in 4 dimensions, you need the three-dimensional spaces, right? Because 3-dimensional spaces separate 4 dimensions into parts. But 2-dimensional space, they don't separate anything. It's like to have a line in 3 dimensions. So what do you do? So it's kind of funny that you can define a cone, a 2D-dimensional cone, just using D-dimensional boundaries, let's say, right? These are not the boundaries, belong to the boundary, but they are not the full boundary, but they determine all the boundary of the cone. Okay, so fine. What is the Voykovsky theorem? Voykovsky theorem says that following, that if the map is symplectic and the cone has this form, if you have this property, then all Lyapunov exponents are different from 0. Half of them will be positive, the other half will be negative. Okay. So that is a much stronger result that allows to prove hyperbolicity of a system. So how does this work? Well, let me just to show to you how this works, let me just do the computation in 2 dimensions. Because the beauty of this idea is that essentially take the d-dimensional, the 2D-dimensional case, and make it essentially absolutely equal to the 2-dimensional case. So if you understand how to do the computation in 2 dimensions, you can do the same computation in any dimension, only instead of having number, you have matrices, and you have to be a little bit careful about what a symplectic matrix in 2D dimension looks like and stuff like that. But apart from that, it's like the computation in 2 dimensions. So let's say first of all, you can check that if you have 2 Lagrangian subspaces in 2 dimensions, let's say that you can always make a symplectic change of coordinates in which the symplectic form is just x minus y x tilde. So this is the standard symplectic form, dx dy. This is dx dy. So you can always take this, or if you want, you can write this as a vector v, j, a vector v tilde. This is a scalar product when j is the matrix 0, 1, minus 1, 0. It's exactly the same. It's just a scalar product. Instead of having identity here, you have this matrix. This is a symplectic matrix that over there. Okay, so you have this symplectic form, and you can always further do a further symplectic change of coordinates in which the Lagrangian space, they correspond exactly, L1 correspond to the space x0, and L2 correspond to the space 0, y. Okay, that means, so the picture is like this, as I did before. This is the cone. Okay, turn out. Because why that is the cone? Because let's compute. You want to compute that omega. So you take a vector x, y. This you can write it as x0 plus 0, y. And now you want to compute omega x0, 0, y. And this should be bigger or equal than 0. So what it is, this is this times that, which is xy, and then this times that, which is 0. So xy positive. Xy positive is exactly this two quadrant, the first and the third quadrant. Okay, so all right. And now the determinant of the map will look like A, B, C, D, with the fact that it's symplectic, but being symplectic in 2 dimensions simply means that you preserve the volume. So that means that the determinant is 1. So it means that A, D minus B, C is equal to 1. That's what it is. And also this one will preserve this cone. This is the assumption. And that means that either all the elements are positive or they are all negative. So let's say that they are all positive. So A, B, C, and D, they are all bigger or equal than 0. Okay. And now I have that so if you want, being strictly inside simply means that if I take a vector d v, okay, this what is going to, it means, okay, so being strictly inside, when is it that a vector is strictly inside the cone? When this one is not bigger or equal than 0, but this is strictly bigger than 0. That is the condition for being strictly inside. So if you want, we can define a quadratic form. This, if you want, is a quadratic form, right? This is Q of x, y, of the vector xy. It's a quadratic form of a vector, because you see it's quadratic. This is bilinear, so it's a quadratic form. So we define a quadratic form, and when and then it is just enough that this to show that this quadratic form increases. Because if the quadratic form increases, it means that you take a vector that is in the cone, so the quadratic form is positive, and then you get a vector that is, as the quadratic form, strictly positive. So it must be strictly inside the cone. So this going inside the cone is like showing that this quantity increases. That's just one alternative way of checking. But another way of checking is just that I want to check that this vector and this vector, they go inside. As I did before. If they go inside, if the boundary of the cone go inside, then I'm done. So I have to compute. For example, let's take this vector. So this is the vector x0. What is going to be is going to be a x. Then it is cx, right? And dt0 y instead. is going to be equal to b y and then dy. Okay. All right. And now I want to compute, I want to see what happens. So this vector here, if I compute for this vector, this quantity, I get 0. This is on the boundary of the cone, right? So I want to see the image. So let's compute the image. This vector, it is, I can write it as ax 0 plus 0 cx, okay? And no, okay. Let's take this. Yeah, I can do this computation, but it's too long. Let's just take a generic vector that is in the y, okay? And then this one will be equal to ax plus by, and then cx plus dy. And now I want to compute q of this. And this one is just the sum of this vector with 0 and that vector with 0, right? So that is going to be equal to the product of these two guys. So ax plus by times cx plus plus dy. Okay. So this is going to be equal to a c x squared plus, I'm sorry, this is a very boring computation, but okay, that's what it is. AC plus b d x y plus b d y squared. Did I do a mistake? B a c b d. No, sorry. No, sorry. It's a d. Oh fuck. A d, and then this is b c. Okay. So this is what it is. But now these guys are positive. This is x squared is positive. These are positive. This is x squared is positive. So this is bigger or equal than this only. And this, you can AD minus BC, it is 1. So this you can write it as 1 plus 2 BC. And then is XY. But this is exactly the quadratic. So this is exactly 1 plus 2 BC Q of the vector XY. I don't know if you can, I'm exhausting the blackboard, I'm sorry. I don't know if you can see it, it's a bit low. Okay. And I can take it up. And so you see, this is positive. So it means that the quadratic form is increasing for all vectors. So if this is bigger or equal than 0, this guy will be bigger. So it keeps growing. And then that means that if you look at Q dTn for a vector, this is bigger or equal than 1 plus something alpha to the n QV. Right? This means that it's increasing exponentially. So from this to check that the Lyapunov exponent must be positive. So that is more or less, I mean, just essentially this is proof of Minkowski theorem in 2 dimensions. You just have to use the fact that x squared, you see, if this is a vector, let's call it eta 1, eta 2, then, I mean, this one is equal to eta 1, eta 2, but this is less or equal than 1/2 eta 1 squared plus eta 2 squared, which is actually the size, the norm of the vector. So the norm of the vector is growing exponentially unless this is 0. But this is maybe 0 at the beginning, but if you do one step, this goes inside and this goes inside, and then Q is not 0 anymore. So you have an exponential growth of the length of the vector. And so this shows that because we have seen that this goes exponentially, and this shows that the Lyapunov exponent is positive. So essentially, that is essentially the proof of the theorem. You have just to play exactly the same game. In higher dimension, is exactly the same. Only these one are D by D matrices. Okay, and then there are some relation between this is the same, and then some has to be symplectic, some has to be self-adjoint. Now I don't remember, but it is trivial to check. And then you could do more or less the same computation, and it works. So that is kind of, I find it a very nice theorem, and is more or less all what we have rigorously to prove that the system is hyperbolic and estimate Lyapunov exponent. And if this does not work, well, then you have to talk to the next, to the other mini course in which in which it is explained how to do things numerically. Because if you don't know how to do it rigorously, then what can you do? You have to just estimate things numerically. Yep, let's stop. No, it's okay. I mean, I'm exhausted. Maybe you are bored, so that's it.
You do the reduction, you end up with T. So
No. But you, for example, in the billiard with infinite horizon, you have a zero Lyapunov exponent, correspond to trajectories that never hit the obstacle. So zero Lyapunov exponent, it can happen if you have one side of the cone that stay put. It never gets in, and then you are in trouble, because you can make a very small perturbation and make this side go outside the cone. And once you are outside the cone, you see, when you are inside the cone, the dynamics push you in and you are happy. But when you are outside the cone, the dynamics push you away, right? Because, I mean, if you have something like that this push you in like this, but now you have this push you in and this stays put, right? So if you are a little bit outside, then this may drift on the other side. That is going to be a disaster. Nothing will work. So that is very delicate. And in fact, there are, starting with the work of Ricardo Magnier, there are results that show that if you do a C1 perturbation, you can kill, and you have zero Lyapunov exponent, and you do a C1 perturbation, you can kill the Lyapunov exponent in the system. Okay. And I mean, Magnier announced this result. He died, unfortunately, died before he could write it. But then eventually it has been written in all the details by Diana and Bob. And so this is not stable. But if you go strictly inside, then you do a small perturbation, you are strictly inside. And that is true also for the second theorem, in which you have Lagrangian subspaces, unless your perturbation is not a perturbation that destroys the symplectic structure. So if you make a perturbation within symplectic maps, and you have that the cone goes strictly inside uniformly, then this you make a small perturbation, and this will survive. And so it means that nearby system will be still uniform hyperbolic. So if you have a uniform hyperbolic system, nearby system will be still uniform hyperbolic. But if you have zero Lyapunov exponent, then I'll get loose. I don't know. I mean, it's debatable, right? Because this result by Vian and Bocchi, they require a C1 perturbation, and you could argue that C1 is not very reasonable, right? Because I mean, the theory of all this business in which you construct invariant manifold and so on and so forth require a little bit more than C1. C1 is kind of the boundary. You want to have that kind of the derivative of the map has some still regularity property. So a more reasonable perturbation theorem would be in C2. And this is not known. If you have a zero Lyapunov exponent and you do a perturbation in C2, you can kill all the Lyapunov exponent or not. That is an outstanding problem in the field. Field is full of outstanding problems. So lots of work to do for young people. I'm going to retire in a little while, so I'm done. But you are not. So Yep, there are a lot of problems that are open, and we have not many idea of how to solve them.
Any more questions or comments? So we resume at 11:30, hopefully with lights on. So let's thank the speaker again.
Great, thanks. So all right, so this is somehow a well, okay, more numerical methods in non-hyperbolic chaos, or indeed hyperbolic chaos. But I just was going to sort of at the end of last talk, which sort of maybe do something a little bit philosophical, which is to talk about how rigorous rigor in numerics. And we've seen, or perhaps, as you know, you can be, all sorts of kinds of, I mean, even in your, also in your calculations that you might do on pen and paper, you can be varying levels of rigorous. Well, these all sort of, how would you say, these all have their place. Sometimes, there are obviously, upsides to being more rigorous, because, you have more, you have a different kind of, you have this kind of, it's true for all time in all places. Like you have that down 100%. On the other hand, it can be more difficult or more work, or perhaps more impossible. And well, that's the sort of nature of work. It's a trade-off. And I would just note that we actually do always make at least hypotheses, even if not, I mean, not theorems, but hypotheses we can make based on some kind of inductive reasoning. I mean, this happens all the time. And I'm just going to fix that. Maybe I can't. Yes, I can. Yes, so we make it all sorts of, let's say, hypotheses that are not necessarily rigorous, but are, something that we obtain through experience, and which maybe we might use in other sorts of places. So, I mean, just to sort of do a categorization of it, we could start by saying, well, okay, I mean, just imagine that we have some algorithm which either is pen or paper, or is on a computer, and it will compute some proposition. And of course, we could have, somehow prove a theorem, and we can prove a theorem both by paper, but also using the computer to say that this is true. Deductively, it's it's something that we've done a logical process that is proving a theorem, and we have seen that it's true. So an example of this in numerics is perhaps a really famous one, but one that perhaps started the whole idea of interval arithmetic really brought it out as something that is used in mathematics, and particularly in dynamics. So what Warwick Tucker did in his PhD thesis was he proved that the Lorentz flow, which is as in Lorentz 63, the really famous guy, the butterfly, is a geometric Lorentz flow. And so, which is, I mean, it looks confusing, but the idea of a geometric Lorentz flow was this kind of sort of class of systems with a certain kinds of with a certain kind of shearing property, let's say. And everyone thought that Lorentz flow was a geometric Lorentz flow, but no one really could prove it. And I mean, somehow what it requires is showing, like you've seen in the previous talk, the idea, also in the mini course of this morning, that cones mapped into inside each other. Basically, he had to show that some cones mapped inside each other, and the way that he did it was using validated numerics, and so interval arithmetic. And I mean, at the time, a lot of people, some people didn't believe that this was correct, and that that this counted. And perhaps it took a bit of time for people to come around to it. But well, it is indeed a theorem, and I think he won some big prize for it. So good on Warwick Tucker. We could also say, and actually also thinking about Stefano's talk yesterday, a lot of what he does is in this category, or indeed what many of us do. But yes, a lot of the stuff in that talk was of that. We could then say, well, okay, let's relax that a bit. And we say, well, okay, we know that our algorithm converges, and perhaps at some kind of rate. And well, maybe we could prove this theorem if we decided, we looked at all the little small sources of error in our, say in our numerical approximation, or perhaps in the, the small error, the convergence, the error here, in A when you do it at some sort of finite size. If we computed all of these, which we know is small, then well, we could get a theorem out of it. And this is, I mean, basically this is what people do a lot, say in I mean, I don't know, like if you simulate your ODE, if you sort of try and run it over some long time period, then you know that, or some medium length time period in just on your computer using your algorithm, this is actually in this sort of category. So you know that you have some theorem saying that, I don't know, like your finite difference method or whatever converges as you send your step size to 0. If you want to say that your guy is in, your solution is in a certain region of phase space, you just have to make your solution small enough. You make your time step very small, and you see that it's in this region of phase space, and you say, well, okay, that's good enough. If you decided to really keep track of the errors, you could prove a theorem, but a lot of the time people don't, perhaps because they're physicists or they're engineers, and so they're just like, well, like, that's fine. Near enough is good enough. Why not? I mean, sort of going a bit further, you could say, well, okay, maybe we want to take some algorithm that we've already used. Let's say I don't know, and just do some like minor twiddle on it. So we're sort of outside of what, say, the theorem that we know that it converges has done, but well, sort of morally the same kind of stuff's happening, and this minor change is going to work. And this happens a lot. I mean, if you're doing research, if you're sort of trying to do some kind of research, like understand something or sort of try and see what's out there, you're often changing your algorithms, or you're often doing slightly different calculations on your piece of paper. Well, then these sort of work, and you reckon they should work, and probably if you had to prove it, you would, with not thinking too much. Well, this is sort of what the sort of kind of, let's say, the epistemological kind of thing you were doing there. You're being like, well, I know that, like, I reckon this is true because I have, I'm some distance away from being like, this is a theorem. This is definitely, absolutely, deductively true. And also we can say, well, what if we, I don't know, slightly relax our Banach spaces, and knowing that this is understanding that this is okay. Maybe. I mean, it really depends on your Banach spaces. I'm not saying this is true always. So actually, at this point, maybe I should say, I'm just giving you some things here, but if you can think about what you have been doing, like, say, numerical, even calculations just on pen and paper that you've been doing, and where they fall into in these categories. I mean, perhaps it's a nice exercise to do, because we're going to get into some ones that are a bit more perhaps a little bit further removed. And this is one that if you were doing, say, non-uniformly, well, if you're looking at stuff that isn't necessarily hyperbolic, and isn't necessarily uniformly hyperbolic, rather, then you sort of start to rely on this kind of thing. And often the clearly true, so that, if there's something that we know is that, like, we can absolutely see it's true, but we just don't know how to prove it. It is an open question. But if this holds, then, somehow we would be able to, we would not be far off from proving that knowing that our algorithm gives us the right answer. So for example, assuming that something that looks like it's exponentially mixing, as Carlangelo was talking to you about a little bit this morning, or indeed yesterday, with this having this, say, this how would you say, this point spectrum, the spectral gap, assuming that this is actually the case, even though we don't know the Banach space, we don't know any of the theory, just like saying that that's what's going on. This is something that we're going to have, like, if you have to do quite a lot if you want to apply the stuff that we develop in hyperbolic systems to more general chaotic systems. And this is another one that we like to do. We like to say, well, okay, somehow in some setting that we know a lot about, so for example, a uniformly hyperbolic system, then, well, if we use this, I mean, there's various kinds of, say, linear response algorithms that so ways of computing derivatives of physical measures with respect to parameters. There are ways, there are people who sort of try and use this and say, they make this argument, that, well, if we could somehow extend the proof of this to the non-uniformly hyperbolic case, then we could, I don't know, we could do something with it. You know, if the non-uniformly hyperbolic case behaves like the uniformly hyperbolic case, then our algorithm is going to do the right thing. And so then they you know, people try and play around with that, me included. And so and then, you know, I mean, if you sort of went and get further away from that, you say, well, we've just done some calculation, and like formally this should work. Well, I mean, maybe we have some evidence, because this is, you know, just saying something that formally works does not mean anything very much. Well, it doesn't necessarily mean anything very much. Well, if we have some evidence, maybe we can guess this. And I mean, of course, this is where a lot of ideas come from. And to some extent, I mean, you know, particularly say in physics or in engineering, and to some extent, there's a certain amount of mathematics that is, let's say applied mathematics, is just trying to, you know, is trying to prove these things that people have just been doing and say, well, yes, this works. I mean, you know, and if you go and talk to an engineer or something, I'm like, of course this works. But you know, then what many people do is they go off and try and study something mathematical about it, which is of course great, because sometimes you learn things mathematically that you don't always learn. How would you say? Something that you wouldn't have seen if you weren't trying to play around with it, you know, rigorously. So I will just say, again, if we look outside of uniform hyperbolicity, because we know so little about these systems, we are always going to have to assume things that we can't prove, or that we don't know how to prove. And that's just life, I guess. So yes, so I suppose nice to think about sort of examples where in your process you have done that. And now I will start talking a bit about actual chaotic, well, talking about the actual topic of this lecture, which is Monte Carlo simulation. So given these physical measures, which tell us a lot about the statistics of our system, long-term behavior, and we also really come into play when we're trying to do other sorts of, I mean, stuff that I'll talk about later about sort of estimating transfer operators, or indeed, you know, looking at their sort of limit statistics. We sort of need to understand something about this physical measure. That should be a row there. Of course, these are measures, so the way that we usually access them, assuming that we don't know any extra structure about them, like, you know, maybe they're absolutely continuous or something like this, the way that we tend to access them is by thinking about integrals with respect to other functions, with respect to actual functions. You know, measures being kind of duals of functions in some sense. Okay, so we would like to estimate this. Let's say we'd like to estimate this for some function A. We can try and do this using a Birkhoff sum. But I mean, somehow the idea of a Birkhoff sum is just that if you take some, you know, you start from some randomly chosen initial condition according to Lebesgue, and you take a, you know, a long time average of A of the future orbit of that, it will converge eventually to this average, but you don't know how fast it's going to be. So one thing, and particularly say if you've got, you know, some system you don't know anything about, you've got no idea how to tell how fast it will converge. So how would you say, we sort of want to do some kind of error quantification, uncertainty quantification is the word. So quantify how big we think our error is for whatever we're using to estimate this. And well, I mean, somehow we need to know some sort of structure here. And the kind of structure we're going to use is assuming that, more or less, I mean, plus a bit, assuming that we have some kind of decay of correlations for against our measure for our dynamics, like we saw with this spectral gap from Carlangelo's lectures a bit. So somehow, yeah, so the idea is, I mean, again, as Carlangelo said, we're going to try and use some ideas from statistics. We're just stealing things from statistics. And what this is going to be is, well, what they call Monte Carlo estimation. Yeah, perhaps a really, actually in some sense, a sort of less fancy version of it. So I don't know, a poker machine estimator, perhaps. So, okay, we have, I mean, the sort of setting is that we have just some measure, some probability measure, and some function A, which is very general. It just has to be, you know, integrable with respect to this measure. And we take some independent samples. So we're not going to think about dynamics yet. We're just going to take some random samples, and we want to estimate this integral. And well, okay, as we all know from statistics 1, there is a so-called strong law of large numbers that tells us that with probability 1, if we take this sample mean of all of these guys, that we will converge as m2 goes to infinity. Great. So that, I mean, that looks like our Birkhoff. Of course, that's like our Birkhoff law. And again, here we don't really have any idea of how fast it will converge. So but we can try taking this average. Okay, so I'm just going to say here is our function. Just say x is 1, and we run it for a long time, and we see that okay, actually great. So we run it for like 1,000,000 steps. And you can see that it's converged to its true value very quickly. And in fact, even if we did 30,000 steps, you can see that it's converged pretty reasonably. On the other hand, but I mean, like, the strong law of large numbers is somehow the most broad convergence result you can get. Like, if you don't have, I mean, somehow if you have L1, it's something that's not L1, then this integral doesn't make sense. So, and if you have something that's, well, I mean, so somehow L1 is the largest category of things for which this even makes sense. And I mean, this is what people call qualitative analysis, which is where you take the broadest possible answer and you just say there is some convergence. We're not going to say how fast. But if we want to quantify our error, then that's kind of not good for us because, well, let's say, you know, if we say we run it again we look at a different function, let's say, I think this is a good one. Yes, it is. Okay. So we look and then, okay, we try and run our sample like this. Well, we get some kind of, our convergence rate here is, well, it's not converged after 30,000 steps. And if we try, there's no dynamics. I'm just randomly sampling, sorry, yes, these IID, yeah, just, sorry, yeah, uniform IID. And this is the observation. So it's A of uniform 0, 1. So, I mean, if you try and draw this, I mean, you know, this, well, if you try and integrate x to the minus 0.9 over, I suppose, 0 to 1, then you see that it's, I mean, it's only just integrable. It's got a very big spike. It's certainly not L2, for example. And if we even try a very long, you know, just have a really big sample. That's not really that big. We can see that it's just not really converging very fast at all. So let's see what this one does. So somehow the strong law of large numbers is actually not particularly useful to us because we sorry, let's stop computing. Well, I suppose this is a problem when you add a 0, you have to wait for 10 times longer. So, sorry, you're lucky, yeah. Well, in this case, it's, yeah, there you go. So I don't know. I mean, like 11 versus 10. What's this spike? So, well, probably what's happened is that it's just randomly sampled a point that's very close to 0. And then, well, some, you know, like, yeah. Exactly. So, oh no, this sounds like we're gonna, here we are. Oh yes, right, exactly. Cool. Important to see this on the slide. Yes. So we want some kind, so actually what we need is, what we know is something quantitative. So we need to make some more specific bound on the regularity of our function A, and then hope that it will give us perhaps, or not the regularity, on the integrability, like on the tails of this function A, and then we hope that we can get something better. Yes, something better to something that will converge at a rate that we can sort of, you know, bound nicely. So, okay, if we start with perhaps a very strong assumption on the tails of A, we just say that A is just completely bounded. There are some constants above and below which A cannot go. This is, of course, very normal for most observables, you know, most functions that you want to think about. And there is a theorem here that says that, okay, a very quantitative theorem. We say that suppose that A is bounded, and in particular, it has this sort of bound. And of course, as we know, then we can say, well, so somehow we also need to bound on the variance, but I mean, the variance can be bounded by this alpha squared. If we do this, then we have something that looks, we can say that let's say that the deviation between like this sample mean and the expectation decays, I mean, has very nicely decaying tails, in fact, decaying like a normal random variable. So somehow what we can say here is, well, okay, supposing that we, and I should actually just say where it works. So here we have, right, so if this was equal to, so if W is small, W times alpha, if this thing is small, then this is approximately equal to 1. So this whole guy here is approximately equal to 1, and this is just looks like a normal. I mean, it's looks very close to the decay of a normal random variable, with the sort of standard deviation that you expect to see in the central limit theorem. And so, well, okay, we can try and estimate this. So here's some function here, and if we just take a priori bounds on this variance guy and what's this guy? And the bound, we can say, okay, well, let's just take a bunch of these sample means. So we randomly generate a bunch of our x's, and we apply our function to them, and we take a mean of that. Well, okay, yes. So, and then we do this, let's say, 100 times, just to see what our different sample means look like. Right. So we figure out some. Then, okay, so the idea of this is that so here we plotted our sample means in blue here, and we said, okay, let's use this theorem to say, okay, well, in this black line, and I suppose it's a bit hard to see from all this, but in this black line, we want to have 10% of our points, 90% of our points lying within this black line, and then 10% can be outside of it. So it's like, because this is random, I mean, somehow you know that you're right, or the thing that you want is, you know, the thing that you want is you're only going to get the thing you want 90% of the time. And okay, so in this case, actually, we have substantially overperformed because all of our points, all of our 100 points, are lying within this how would you say, within this sort of confidence interval, or rather within, yeah. So all of our sample means lie within this bound here of the true mean. So this is the true mean, this guy. But we can sort of rethink this a bit, because what we're saying here is that, or indeed what we have in the theorem, is that so what I was saying there is saying that that these sample means are close to the true mean within some given bound up to some tolerance. We can also say that, well, okay, with very, very high probability, the sample mean is, so the expectation is actually close to the sample mean within some bound. So this, I mean, this is the idea of confidence intervals in statistical testing. And so we say, okay, I mean, we'll just run this experiment 100 times, and we say, okay, here is these blue dots here, if you can see them, are a bunch of different sample means. And you can see that, okay, basically, again, basically every time, our sample mean here is, how would you say? Sorry, so the true expectation, this thing that we want to get out, this average, is always within this sort of bound here that we sort of pull out from the theorem. So somehow, you know, if we say, well, okay, If we say, well, okay, we'll pull out, we'll sort of sample from this measure a bunch of times and try and estimate its, and take some sample mean, and then we say, well, you know, allow ourselves some tolerance, then we're always, at least here, we're always going to get it right. Although our theorem says that we should get it right 90% of the time. But, you know, somehow it is often, because this convergence is really quite, this convergence is really quite slow at some level, that we needed that the sort of size of these error bars go as a square root of order 1 on square root m. I mean, it's just, you know, like the central limit theorem. In fact, we will start talking about the central limit theorem in a bit. Is not this, yes, yeah, there is, yes. But this is a sort of weaker version, like a weaker, more, I mean, yeah, more quantitative, more ironclad version of it, because we actually, I mean, we really, so the central limit theorem is giving you a sort of limiting, saying as n goes to infinity, but here this is actually for finite m. Yeah. Right. Yes. Yeah. Yeah. So I mean, if you pull it out from here, you get oh, did I do that right? No, I did not do that right. Yeah. You sort of, this is the size of this scales like sigma on square root m. Okay, yeah, right. But I mean, somehow, you know, that is actually, it means if you want to get like an extra digit of precision, right, you have to, you know, multiply your, you know, increase your sample size by 100. So it's really, and if you want to increase, you know, your precision by half, you have to multiply your sample size by 4. So you know, you're running your thing for 4 times longer, and this can be really annoying and tiresome, and eventually perhaps you hit the limit of what you can actually do with your time or with your computing power quite quickly. So statisticians actually really have this, maybe they're less into it now, but I mean, they really used to have this thing for trying to find like the optimal bound that you can, and like trying to make things as optimized as possible. So for us, well, okay, one thing we could just do is we could say, I've just got to remember what this was called. That? Yes, okay. So for us here, we could actually, I mean, just imagine that we could just estimate, well, we knew the true variance of our thing. I mean, this is not very realistic, but we could just try and tighten our bounds here because we were assuming we had some extra parameter here which bounded our L2 thing. Well, okay, I mean, the sigma squared here. So to make it kind of optimal in some sense. Okay, so if we do this, we actually see that we get better convergence. If we really do know the variance of our system, as opposed to having some kind of perhaps quite bad bound on our variance of the system, of our sample mean, then we can see that we can actually get much narrower confidence intervals that perhaps don't include all of our points, but that's fine because we're just, you know, our theorem only tells us that we get the right answer 90% of the time. And you can see here that, well, yeah, we sort of get a much, well, no, rather when we do this guy here, we get a much tighter estimate on our confidence intervals. We know, so we have, if we did not know this black line here, we would, and we just looked at one of these, we would know, we would have some, you know, information about our guess, about our sample mean, true mean rather, a lot better, like more tightly. Of course, somehow even this is not optimal. So this is why this, at some level, why the central limit theorem is famous and is what people really like to use in statistics. And well, I mean, I'm sure we've seen it all before, but basically what it tells us is that as a sample size goes to infinity, the deviations from the sample mean, from the true mean of the sample mean, behaves like a normal random variable of variance, well, sigma squared on m. So sigma on a variance sigma squared on m. So square root. Now this is how would you say, this is a sort of rather qualitative at least result in its generality. If you know that A is also bounded then you can make some sort of more estimates, but I mean, perhaps that's a bit too much. And so when people, well, let's say when statisticians like to use this in statistical tests, they make some, let's say some assumptions, not assumptions. They make some, guidelines for how you should use it that are not, I mean, they're not completely mathematical, but they're sort of, they seem to work quite fine. So we can say either, well, okay, we have M is big enough, and the tails aren't too terrible in some sense. Like, you don't have a bunch of points out at, 1 billion that you just, that will break your central limit theorem. And perhaps also that, but basically you want M to be reasonably big, or perhaps you want this distribution here to already look like a Gaussian. So for example, if A is, if the distribution of A is in fact a Gaussian, then this is not a limiting thing, this is always true, right? Yes, but perhaps if we want to be really cautious, we will want both of these to be reasonably true. So indeed, if we do this, look at our, what is this? Yes, okay, so now if we actually, look at our, take these sample means, but now we use this idea, and now I should sort of explain to you what's going on here. So if we say, okay, we want our sample mean to be, I don't know, like say like theta close or theta on square root m close to our sample mean, say our true mean, then, well, okay, let's say we want it to be close 90% of the time. So then we want this here. Well, if we want to be close, we actually need to think of it as in a kind of two-sided way. So we could sort of be a bit more specific here. So we could now think about this average, but then because it's two-sided, we need to put a 2 here. Okay, so then if we want this to be less than this 90 like 90% of the time, then we would want to equate this here to 90. And if I did this, so this is what I know here I actually made it 95%. Let's make it 90%. If you do that, you can see that okay, somehow we've taken a bunch of sample means, we've done a little confidence interval on them, which is what this kind of this is the sort of amount, this theta on square root m. You can see here that, well, if we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, it's about 10. About 10% of the time we have got our we've managed to estimate the true mean kind of correctly within our tolerance. Of course, 0.1 is a bit perhaps not what you really want to use. Let's say 0.01. And then we can see that, yeah, pretty much once it doesn't work. We've got the wrong answer. Or rather, the true answer is not within the tolerance of the answers that we allow. Of course, there's a bit of a problem here again, which is that we don't actually know this true variance. Where do we get this true variance at? Oh, this W. Yeah, right. So I've actually just put in here. So this is trying to find this this theta. The theta is this guy here. So I mean, using your favorite statistics package, you try and, well, you type in a command like this, yes, so here I've actually put in the true variance, but of course we can't always do that. And okay, again, we can just use some ideas from statistics. We can estimate our standard deviation. Okay, so this is actually already the variance, which is the standard deviation squared. So this is an unbiased estimator of the variance, and it looks like what you've all seen. You've probably seen this before. But the nice thing about this estimator is that if we actually try and approximate, so if this was the true variance, then, or the true standard deviation rather, this would be proportional to so this would be distributed like a Gaussian, but it turns out that if you plug in the sample variance, it's distributed like a t-distribution. And I mean, what is the t-distribution? You go to your favorite free online encyclopedia, and you look up your distribution, which is, I mean, I think what everyone does when they discover a new distribution. And you can see that it actually looks a lot like Gaussian distribution. So this here is what's called the number of degrees of freedom, and you can see that it's sort of, I mean, as the number of degrees of freedom goes up, so that is to say that your estimator is based, your variance estimator is based on more things, it starts looking like a Gaussian, but before that it's got kind of heavy tails. And well, okay, using this kind of distribution, we can essentially try and generate these confidence intervals, really knowing very little about our initial distribution, except that it's not nasty. So just to explain, we take X vector. So we generate a bunch of sample points. We take the sample mean, and then we also take the sample standard deviation, which is square root of the sample variance. Well, we compute this kind of quantile thing here. So this is like the amount we need so that oh, 0.05, is it? So it's this guy here, and we do that, and well, we try it, and we can see that again, not knowing anything about the true variance or anything we can get about, well, I suppose 5 and 100 of these guys to be wrong, and more importantly, 95 and 100 of these guys to be right. And again, we could just try and make that a bit better, whatever. And that will lengthen our intervals a bit, but not by much. So somehow, if you were sampling, I mean, yeah, if you're doing random sampling, this is what you should be using. And I'm sure I bored you all to tears with this basic statistics, but we're going to apply this to understanding sampling from physical measures, or I mean, really sort of any kind of measures that you can sample dynamically. But I mean, that's going to be, unless you do something very fancy, it's going to be a physical measure, as I talked about last lecture. So basically, the idea is we want to sample from our measure rho, but I mean, sampling from your measure rho is a bit, getting IID samples from that is perhaps a little bit complicated. So perhaps we just want to sample from something whose distribution is like this. And one good candidate for this is, in fact, these Birkhoff averages. So you look at, let's say you take X from some initial distribution mu, and of course the natural one for that to be would be something that's absolutely continuous with respect to Lebesgue. And you know that, well, as n goes to infinity, almost surely the expectation of this, so you, well, no, almost surely this will go pointwise to converge to this expectation. That's just the Birkhoff-ergodic theorem. So, you know, maybe we could sort of try and, so we could perhaps then say, okay, therefore the expectation of Bn of X is going to be close to, is going to be close to this because we have this pointwise convergence. That's not always, and then we can use the central limit theorem is the idea, but we don't actually always know that's the case, because almost short convergence is not the same as n goes to infinity is not the same as convergence in expectation. You could imagine that when you do your Birkhoff averages, you have this problem. Okay. Good. Thanks. When you do your Birkhoff averages, you have something that looks like you have something that's, you know, a bunch of things that are nice and converge to the true value. Thank you. But then you could also have something that goes off and does something completely terrible, and something else that goes off and, you know, so it may not necessarily be the case. Or maybe it is if it's bounded, but if it's not, it isn't. But we also don't know the rate of convergence. So we need something to sort of give us this rate of convergence. And well, the kind of, I mean, going back to this idea of rigorous, we need to use something that we can obviously, we know is true. And perhaps sometimes you can prove this, but often we can't. And the thing that we know is true is decay of correlations. So this comes down to this idea of I mean, Carlangelo talked about it a little bit. Often the way that we prove this is by saying that the transfer operator has some nice spectral behavior, but basically we can say that the correlation between two functions a and h, as n goes to infinity, is going to look like, if it's aperiodic, if there's no periodicity in the system, then it's going to converge to this plus something here that decays exponentially quickly. But there may be some periodicity in the system, and so you could get something, a set of guys here that look periodic. So I will just, no, hang on, we can turn this over, can't we? Perhaps try to explain to you where this expression comes from. So you imagine that you have your unit circle in the complex plane, and you know that you have, well, okay, you know that your physical measure has, which is like your absolutely continuous measure, has eigenvalue 1. You know perhaps that there's some essential spectrum, not so important, and then you know that you have isolated spectrum everywhere else. And perhaps you might actually have some isolated spectrum on the unit circle. But in this case, you know that this has to be of some complex, these have to be on some complex roots of unity. So, which we'll call xi, to have, like xi squared, xi cubed, xi to the fourth, whatever, like this. And so you can write your transfer operator, you can decompose your transfer operator as, I suppose, well, whatever you have at this eigenvalue 1, the projection at the eigenvalue 1, which is somehow your invariant measure times some, let's call it some operator I, so that I of phi is just the integral of it, plus some projection guys psi to the pq plus some operator, some remaining operator q, so that q, or the spectral radius of q, looks like this, and your projections here are projections there as well. And so this here is also being a projection, but we know that the integral of rho is 1. So then if you then take the fact that this correlation, well, it's not quite a correlation because it's not normalized to mean 0, but if you do this, then this is the same as L to the n of, sorry, A times A integrated by L to the n of h dx. And then you just apply this argument here, and to first order, so this first part here gives you the integral of A times rho times the integral of your I didn't use mu, I used h. Okay, your measure mu here, which you can think of, I mean, so somehow in the, say in this uniformly expanding case, the set of nice measures here are going to be things with densities, but they don't necessarily have to be. Actually, we can write this as so. And so once you sort of follow this out, you get some behavior like this, and I shouldn't use q there twice. We'll use this as k or something like this. And these constants here are just somehow the integrals between h, a, and h, yes. Yeah, no, sorry, that I got a bit, sorry, that should be d mu. Sorry. Use the starting measure, yes. H, let's say h is, man, okay. H is this sufficiently nice measure. There we go. Sorry, I should have edited the slides a bit more. But yeah, I mean, you can imagine it as a sort of default that, yes, it is. Well, not necessarily. I mean, I haven't said that. I haven't stipulated that that it is here, right? So, but yeah, it's not a problem. Well, I mean, yeah, it will be a probability distribution, so you can imagine that that goes. Yeah. And in fact, if you do, you can see that, well, if we use this, we can actually estimate the expectation of this guy for finite n. And so if you swap the summation and the integral, you can see that you can use the previous thing to see that the first bit we get is 1 on n times the sum of this integral, which is the same always. For the second, for this periodic part, we get, well, the sum of these, I mean, we're then summing this over n, and you get a geometric sum. And so you just use your geometric sum formula for each value of q, and you get this kind of expression here, which you can sort of see, but I mean, I hope you can imagine is bounded for all n, because this is just, I mean, this guy here has norm 1, so it's just kind of rotating, and it in fact is 0 if you choose n to be proportional to p, because where are we? Xi to the power of qn, if n is like, you know, I don't know, like n is like, if n is some n1 times p, then this is just psi to the p to the power of n1 times q, so that's just 1. And then 1 minus 1 is 0, so this all goes. So you get something here that's bounded, so here that decays as 1 on n, and then also something here that is sorry, it's bounded and it's 0 when n divides p, and well, p divides n, sorry, and this thing here, which well, the sum of qn is we run out of space there. This sum here, which is qn, sorry, which these are exponentially decaying, so the sum of them is always going to be bounded as you take n to infinity. So this here is also order 1 on n. Look a bit ugly here, but okay. So somehow our Birkhoff sum here is like 80 rho plus some error here that decays. Okay, so if we want to code this up, this is the function you do. You need your map, you need your observation function, and you sort of want to initialize it. So you initialize it, you run your system a bunch of times, and you add to, I mean, you sort of at every step you add your function a, and then you divide it in. It's really, I mean, it's really simple, as I'm sure you all know. And if we do this, what's going on there? You realize that some that's a problem. Okay. Sorry, yes. If you do this, well, okay, we can try and do this, and we find that we get some, or we can get some kind of estimate for our Birkhoff mean up to some error. And well, if we run this many times, perhaps we can get some really good estimate of our Birkhoff, of the expectation of our Birkhoff mean. But the problem is the expectation of our Birkhoff mean is actually, well, it is not exactly. It is in fact order 1 away from our guy here. So if our Birkhoff, if our runs are not actually very long, like the dynamical runs are not very long, then when we try and do the kind of central limit theorem sample mean stuff that we were doing before, well, that's fair enough. We're actually going to get the wrong answer. So in general, you want to do a lot of, take a bunch of Birkhoff averages of quite a long length, and then you want to do this a few times, kind of independently of each other. And then you can say, there we go. And then somehow n being long means that your Birkhoff mean is quite close to your true value. The expectation of your Birkhoff mean is quite close to the actual integral of your function with respect to the physical measure. But then because you've done a few independent runs of it, you can actually do some kind of uncertainty quantification on this error without needing to know too much about the sort of deep history of your, well, you know, the too much about your Birkhoff mean, about your dynamics, you know. And indeed, but I mean, there are various reasons why you might not actually want to just immediately start running. So before we started using Birkhoff mean, starting from some zero, starting from just some distribution that is not your physical measure, you might actually want to run your system for a little bit so it starts looking more like the physical measure. And then that will actually, in fact, give you, once again, I have written equations that are too long. Okay, does that look better? Yes. Okay, so, you know, somehow when you iterate your system a few more times, somehow that's like iterating your I mean, this means that all this spectrum here, I mean, you don't see all this spectrum here. It kind of washes out of your mu as you run it through, and you just get, so this thing here is of order, because we're taking Qn plus n naught, this is like times lambda to the minus n naught. Sorry, I should have edited these a bit better. Yes, so we get something here that's actually, you know, if n naught is, you know, 1,000 or something that's pretty easy to do, or 10,000 is usually better. We get something here that's like absolutely tiny. We get this here, and this is still of order 1 on n. But if we, you know, if you run it for a little bit and you notice that you have some periodic component in your system, like I mean, I think we saw it a little bit in my last lecture, briefly, where sometimes it is possible to get a chaotic system that is not mixing because there's a bunch of sort of components that it kind of runs periodically through while within those components being chaotic. If you get that, maybe it's better to take your Birkhoff sum length to be a multiple of that periodicity, if you can see it. But if you don't, you really expect that this Birkhoff sum, your Birkhoff averages are very close to the true guy. And okay, once again, okay, so now the way we've changed this is that we have now included some sort of spin up time. So yeah, you just first run your system for a bit to let it kind of equilibrate. And really what you're trying to do here is to actually get your system to the sort of distribution of this x, so to look a lot more like the physical measure, assuming you have no periodicity in it. And then, okay, then we can do this, and come on, gotta actually run this somehow. Thank you. If we do this, we see that, yes, we can actually approximate this average here. It's true average of a logistic map. So somehow, not, well, I mean, for example, actually kind of a bit of a pain to get with transfer operator methods. We can get this to, well, probabilistically with some very high accuracy. And what's going on here? Yes, it's also kind of, I should also say it's kind of important to spin things up correctly if you, why are you there? Shouldn't be there. Yes? Right. Yeah, there is, that's the true, there is a bit of a lie. It's not, it was simply what I got by running an even longer Monte Carlo you know, even longer time series. Yes, so somehow, yes, there's, you know, it is always a thing that, let's say what you're going to get here is like the value you're going to get is always just the thing that you will see with your numerics, whatever numerics you use. Well, yeah, but with the Monte Carlo thing, the thing you're only going to see is the thing is the system you're simulating is the system that your computer is running, which is, you know, on in floating point and so on and so forth. So yeah, it may not see it, but you hope that it does. I mean, we've argued that you can simulate things and get the right answer. So you can run your system and get, you know, something that looks, some behavior that looks like a physical measure. But I mean, again, you know, thinking about stuff from last week, if you remember this logistic parameter here, where you had this periodic orbit, it took a very long time, that was stable and attracting, but it took a very long time to see. If you also need spin up to deal with this sorts of thing here. So here I ran it with no spin up and not a 0. I just started with Lebesgue and took a Birkhoff mean from that, and you can see that it is a very long way from the true Birkhoff mean, which we do actually know exactly in this case because it's a periodic orbit, and you can somehow the physical measure of this, as we've seen, is just a discrete measure on the periodic orbit. But if we make r n0 much longer, well, actually, this looks kind of weird, right? I mean, we'd expect, well, okay. In previous times, we've seen that all these, the widths here, the kind of estimated variance of our Birkhoff mean. Well, in fact, we expect the estimated variance of the Birkhoff mean to always be the same, but here it's estimating a bunch of different variances. And this is because some of the time it's found the physical measure, which is what's going on here. It's found the periodic orbit, but it's most of the rest of the time is still sort of bouncing around chaotically. So, I mean, if you do see something like this, well, I mean, if you run your system a bunch of times and you do see something like that, then you know that something's gone wrong. So you need to run your spin up a bit longer, and perhaps while we're at it, you may as well make the length of the n better, and hopefully we will see something nicer eventually, 100 years from now. Right. So yes, I should say they often seem to work, but they don't always work. There was something I wanted to say here. Ah, yes. One thing that is actually very nice about this method is that it will work, and I wish I'd actually given you examples of something where it worked. It will work for something that is not the logistic map. It will work for something of arbitrary dimension, and as long as you still have exponential decay of correlations in that system, that's still wrong. Oh, yeah, the scale probably is different. Yeah. Okay, I mean, yeah. Okay, so this is okay, right. So this is up to order 10 to the minus 7. Okay. Yeah, so it's found the periodic orbit and it's converged very quickly because Birkhoff means converge faster for a periodic orbit, and let's say it's an exercise to show that. Or it will be something that, if I have time, I will talk about at the end. But yes, so I mean, somehow this is just all gone wrong because it's not actually chaotic. Well, at least the error functions have gone wrong a bit here because, and sorry. Yeah, exactly right. I think it's okay, right. In this case, it's biased because of the. I suspect that it's biased because the because, you know, perhaps not every run here will have given you will have actually found the periodic orbit, and so sometimes it's already been in the periodic orbit for a bit. So if we just run it, I don't know, maybe it needs to be, instead of 1 million, it needs to be, you know, let's write this time. It needs to be substantially longer. But anyway, I mean, somehow we probably don't want to sit here just waiting for simulations to run. We can all do that when we're back in the office. So I should give you another example where it sort of doesn't work. And this is for a system that, in fact, does not have exponential decay of correlations. In fact, has very slow decay of correlations. So why are we sitting here thinking? I'm sorry, I've done something wrong. Oh, I need to stop that. Oh dear, oh dear, oh dear. Oh, here we go. No, that was just the same thing. Okay. Apologies. Okay, so yes, so we have this kind of LSV map, and if we run it, well, okay, this one doesn't have exponential decay of correlations, and you can see here that well, all our Birkhoff estimates are really quite crazy. If you count it, you should see, no, I don't know. Seems like it almost does work, and I'm mildly irritated about that. That's my fault for not checking it a bit more carefully. Yes, so in this case, we find actually that generally we're not reliably estimating it, or we are, but only for certain parameters. And what's going on there, in fact, is that our Birkhoff means are not normally distributed. So if we plot our Birkhoff means, we see that we get something that looks like this. And I mean, theoretically, it's a Gaussian, but it actually has, if you think about this as the sort of width of the Gaussian, we should see very, very little out here. But in fact, we see a lot of points a long way away. So if we plot it on a log scale, you would expect to see something that is, come on. Okay, right, again. Yes. So I've taken Birkhoff mean m times, and I've done 2,000 of them. We see here that we have something that, I mean, should be kind of parabolic here, but in fact runs off to zero quite a lot. Sorry? No, it won't. It will satisfy a stable law. A is still x. I think it's still x squared, yeah. Let's see. Yeah, A is still x squared. No, A of x is x. We could change this actually. Let's try it, 0.9. If we run this, don't worry about the true LSV mean then. If we try and do this, we will get something even worse. But I should qualify this by saying that the LSV map is not a very it's not a map that, well, I mean, it's a map that you will see if you try and run the LSV map. It's somehow a limiting case where you're just kind of just at the transition to chaos. And if you're not at the transition to chaos, you will see something comparable, but you will not see the so if I mean, you will never actually be exactly at the transition to chaos unless you go and seek it out. But yes, if you do that, if you do go and seek it out, you might see something like this, and it's kind of hard to, I mean, imagine something that this is actually reliably estimating with 95% precision. Yeah, LSV map a problem, but it's not actually just the LSV map, and don't think I can. I should just say though, you might get this if you have a perfectly nice chaotic map, but your observable is nasty. So in fact, what Carlangelo has, I think, mentioned is the fact that you only get exponential decay of for exponential decay of correlations. So that is to say that A composed with f to the n times A 0. Right. That this somehow when you do transfer operator stuff, you need that this lies in some Banach space, and I should explain to you what this is all about. But yeah, here you can see that you have something that is not Gaussian. So yes, so we can ask ourselves what makes Birkhoff means Gaussian and what makes them not Gaussian. And for this, I am going to go to the blackboard. Yes, this converges to this as you take n to infinity. And what this is sort of telling you is, if you think about this as an expectation with respect to the measure, that this becomes, so it's like you've randomly chosen sample from your measure and you've compared B and the sort of future value of A. It's kind of like these guys are independent. That what's happening at A, what's happening to A in the future, let's say, and what's happening to B in the present, which we could also, if we just set A to be a bit more precise. So somehow what they are doing is they're becoming uncorrelated, and this is sort of like a how would you say, an L2 version of a sort of linear version of saying that they're independent. If we had to, you know, with respect to some probability measure, if we had two events and the expectation was equal to probability of A and the probability of B, we would be saying that, like, if this is true for all A and B, let's say in L2, with respect to the probability measure, we would say that this was the same thing as saying that A and B are independent. So, kind of, in our case, these two are not going to be independent because we're in sort of the world of deterministic chaos, and perhaps you may be able, you know, if you know the value of A, like A of X, that specifies the value of X, you know, like there are only a few values of X it could give you. Supposing that you know, I mean, actually, supposing that you know enough about A, like, you know, supposing that gives you a finite number of X's, then that tells you there's a finite number of values that A composed with F at the end could have. So it's not really independent, but considered in some weak sense, we have this sort of independence. And this, therefore, makes us think that if we take a sum of a bunch of these, perhaps this is like taking a sample mean, in some sense, that it's a bit like taking a sum of a bunch of IID variables. And so this might possibly have a central limit theorem. This is the idea. And in fact, this is the case. If this happens, let's say, if this happens, then at least morally, it implies this. And so I hope Carlangelo, I had said that he was going to talk about limit theorems. I'm going to blame this on him, given that he's not in the room. Okay, well done. I won't then. I will simply say that it was silly of me to have relied on, to have hoped at least that someone would explain this, but more or less, it is in fact, let's say, a theorem for, let's say, uniformly expanding C2 systems on the torus, such as we have seen. Right, yes, that in fact, the limit as n goes to infinity of the probability that, we call this the Birkhoff mean of X, the probability that this minus the expectation of it, so rather than the expectation of A itself, so the probability of this is bigger than, let's say, sigma on root m, let's call it sigma squared f of A. Sigma f of A is just the probability that a normal random variable is bigger than theta, bigger than theta. So the distribution of this guy, appropriately renormalized, converges to a normal a Gaussian random variable. And I should say, with this guy being given as, in fact, if you compute just perhaps a nice exercise, if you try and compute the variance of this, and I should say it is certainly a theorem if for x, initial x, distributed according to the physical measure, you can compute that the limiting variance here should be given as a sum of correlations like so. So n equals minus infinity. This is somehow a very nice thing. And I should also say that this is positive, unless A is what we call a co-boundary. So unless you can write A as a difference between two function, between a sort of composition of a function and itself. I think with, and you should correct me here, Alexey, do you need that this is, should just talk about regularity for all A and C1. If A is in C1. Okay, because it's on the torus. Okay. Does it mean it's not 0? Ah. Yeah. Yes. Okay. That would actually make it easier to write. Boom. All right, here we go. Good. All right, there we go. Okay. And so then because A is 0 mean, this thing here should converge, you know, because it's C1. So because it's uniformly expanding, we should get this as n goes to infinity, or plus or minus infinity, but we're taking an absolute value here. This should converge to 80 rho, and these are both 0. So yeah, this here is converging exponentially fast to 0, and well, that's great. We get a central limit theorem, and this also works actually. You still get a central limit theorem if you do have some kind of periodic components. In that case, I suppose you can't say that. You have to remove the periodic components from the correlation function, but somehow this works for things that have this kind of quasi-compactness behavior. I suppose I'm not going to say too much about yes. Up to some accuracy, yes. So one thing that changes is this is not the variance of A for a given, you know, like this is not the variance of, well, I suppose A is mean 0 here. So it's not, this thing here is not this because it's correlated. But you can reliably estimate it, yes. And so the way actually that I've been talking about estimating it in the slides is actually just taking a bunch of different values of this, and then this, you know, because this is a normal variable, you can, you know, estimate it. You can do you can estimate the variance nicely. You can do a t-test, and you can do it all quite pleasantly. That you can use the estimate, you can use an estimator like that, yes. but it's in practice it's not very good because it's, I mean, well, if in a pinch you can do that, but it does cause you a bit of problems, because if you want to estimate, wait, so you're suggesting that we say that A composed with f to the n, A d rho is equal to, or like say is estimated by 1 on n of x. And then you do that for all the different n. It's not so good because this here in itself has got some error. It actually, the error looks something like, well, it's going to be of order 1 on root m. And then if you sum up, sorry, 1 on root n, should two different n's. So this is the length of your Birkhoff average. But then if you're going to sum it up a bunch of times, truncated at order k, then I suppose you've got to sum over k. You've got to, well, firstly you've got to do this sum k times. So it's like you're not just taking your simulation, but then you're running it, but then you're kind of taking a bunch of averages. So to estimate this needs approximately kn computational power. Then you're going to get some error that is of order k on, say, root k on root n, because you're adding a bunch of, so order some power of k. It is actually root k, I think, on root n, because you're adding a bunch of, I mean, you have k lots of random error in there. But if you do this, if you just run a bunch of time series, like I was doing before, you'll have error. Your error will be, well, okay, actually, there's two things to say. Yeah, you take an average. If you run, let's say you run, but you're not running at k. Well, I mean, you're not running at k times though. You're actually, what you're trying to do here is you're trying to compute every term in this sum. This is what not to do. You're trying to compute every term in this sum, or at least k terms in this sum. With this, let's say with the same data, but somehow you want to, let's say you have a sum of k and then you have a sum of n. It actually makes a lot more sense to swap n plus k. It makes a lot more sense to swap these two, because then you sort of want to block up your times. Somehow here you're pulling apart, you're like trying to, you're pulling apart a sum here, which is, I mean, the actual true variance of your Birkhoff guy is like, let's say a sum over k up to k, a sum over n of a composed with f to the n plus k times a composed with f to the n. And so what Kasun is suggesting is you compute it like, you compute this. So you have to, so this takes order kn steps, right? And you get an error that looks like this, plus the kind of extra terms that you've truncated here, which are, well, yes, they are exponentially small, yes. But I mean, then you have to also think about what the decay rate is. But the thing is that if you compute the variance of Bn by just taking Bn, let's say you take Bn, you approximate, you do this guy. So you take the sample variance of Bn 7 times. The error here is 1 on root m. right, and it takes order mn times. But you can use this T's test, which says it actually doesn't matter what the area here is, because that's kind of taken into account with, I mean, yeah, it just means your tails are worse, but it doesn't really matter that your tails are worse. Actually, at some level, you don't actually need this to be particularly accurate. This is order mn, but it actually isn't really. It's of order m plus the time to get Birkhoff means. Which you already have to do. So you may as well just do this. And I mean, you know, you can, yeah. This method, no. I mean, maybe it slightly is, because you need to take multiple independent runs. Whereas perhaps if you use this, you could just take one long run. But it's just like you're just chunking it. Like you just make your runs smaller, because the error you get on your minus sort of, you know, the bar of this Birkhoff means, if you do it m times, the error here is of order, well, 1 on root m times the variance of the Birkhoff mean, which is sigma squared. So sigma squared of a on root n. So, you know, if you decide that you actually want total length n, and you make your runs shorter, then this error here remains of order 1 on root n, which is what you would have got if you just took rows. They're the same. They're the same. Like the variance is the same. But in this case, you have better estimates of this. And also, I should also say, this is not necessarily the same. It's close to, but it's not necessarily the same as sigma squared f of a. The error here is, plus a 1 on root n term from the, from this, if you actually try and compute the variance of this, you'll see that there's the error between this, the difference between this and this guy, this kind of infinite length variance is order 1 on root, or is of order 1 on n. And sometimes this can actually sort of make your, if you're trying to do like some really kind of careful statistical tests with this stuff, which I perhaps would have liked, couldn't talk about, then it actually, you actually do want to estimate this, not that. But this is, I mean, sort of finer details. You want to take Birkhoff means, and we want to take a few of them, and then you want to do sort of central limit theorem kind of style confidence estimates on that, and that is quite reliable. As long as your dynamics are doing the right thing, that is quite reliable. I found, at least. So I think that's in it.
Are there any questions? So can you sometimes have a faster rate of convergence than this?
Yes. So if you don't, well, I mean, if you so for example, if you have this co-boundary wherever it is, if you have something here where A is actually equal to BF minus B, then you can do a little calculation to see that the error is order 1 on n. But that's, I mean, that's really unlikely. I mean, you must have really gotten, either you must have tried, you know, it's like, you know, there's a cliff and there's no, I don't know. It's like there's, you know, a giant continent that's very flat, and there's like one snake pit in all of the continent, and you find yourself in the snake pit. You either got so unlucky that I mean, what are you going to do? Or you're actually trying to find the snake pit. One thing where it can be fast is where you have periodicity. So you know, if you think about you found a periodic orbit, and I don't know, let's say our periodic, like, you know, A of, so here's just some silly version of your periodic orbit is, let's say A of alpha of K mod, so n mod some period here. If you take a Birkhoff sum, Birkhoff mean, then you can see that this is just, I suppose, you're going to just sum a lot of periodic guys. So if n is equal to, let's say, n1p plus n2, you get, you can write it as n1 times the sum of alpha of n up to p, like it's because it's just repeating. If you know, you get alpha of 0, alpha of 1, alpha of 2, alpha of 3, alpha of 4, up to alpha of p minus 1, and then you go back to alpha of 0. And then you have your sort of remainder here. Right? Then this guy here, well, how would we say? You get sort of 1 on p. Well, you get, this is n1 minus n, so it's sort of like 1 on p plus, I suppose, n1 on pn minus that. So these cancel, plus n1 on n. So this here is very small times 1 on p times, oh my gosh, I'm sorry, I'm just, if you mess around with it, here we go. Sorry, this is 1 plus n2 on n times this average plus 1 on n plus something here, which is 1 on n times a sum from n to of length n2. Some stuff. Basically, you get the sort of mean here, alpha of n plus order 1 on n. Let's say order p on n. So here you have a periodic thing, and it will converge. This Birkhoff mean is going to converge to some limit here, which is going to be the physical, this here is going to be the physical measure of this periodic orbit, plus something that decays as order 1 on n. Yeah. Okay. Yeah. But this is I mean, this is actually kind of comes into testing for, this is actually something that's used in testing for chaos. There's this thing called the, well, I mean, it's called the 0-1 test for chaos, which was by Walden Melbourne in the early 2000s. Sorry, well, that's Georg was my PhD supervisor. And so they actually exploited this difference here between the behavior for a chaotic system where you had a central limit theorem and the behavior for a periodic system where you have a 1 on n behavior, to say, well, okay, if you take some Birkhoff sum, perhaps you twist it to make it, try and make it, remove an expectation in some way, then if it decays like order 1 root n, then you have something chaotic or something random actually also. But if it decays periodically like this, because if it decays as 1 on n, you have something that's not periodic. You can actually massively improve this convergence, but I probably don't want to go over time. You can massively improve this convergence if you include some function here, say phi of n on n, where phi of n on n, phi of where the graph of phi is smooth. So it's C infinity going from 1, 0. So that this is phi. Phi is C infinity. The integral of phi from 0 to 1 is 1. If you use this, and so there are many such cases, if you use this, and actually this convergence, I mean, you have to do a bunch of you have to do a bunch of calculations, but it turns out this convergence is actually order super polynomial. Then so you know then it so this is, say, work of Diagnon and Mies. That is a reference I know. D-U-I-G-N-A-N. Yes, that's who that's like. Yeah, I think that's actually the correct reference. So yeah, in this case, if you do, and if you do it for this kind of weighted Birkhoff mean for the chaotic thing, you still get a central limit theorem. Although I don't think that's been proven yet. Someone should do it. Right. So, and in this case, you get a dichotomy where if you have a chaotic system with this weighted Birkhoff sum, weighted Birkhoff average, you get order 1 on root n. But if you have periodic or like non-chaotic behavior, deterministic non-chaotic behavior, then you get something that decays like super fast, like faster than any polynomial. Maybe stretched exponential or something like this. So that's a very easy thing to distinguish.
Are there more questions? If not, then let's thank Caroline again.
And thank you very much. Thank you very much for the opportunity to give a talk at this workshop. So as Julia said, I'm going to talk about globally coupled Anosov diffeomorphisms. And this is a joint paper with Vaal Bassoon and Carlangelo Liverani. So first, as an introduction, I want to explain the words in the title. So first of all, what is an Anosov diffeomorphism? We have a manifold, which is a compact D-dimensional, where we assume D to be larger than or equal to. So it's a compact Riemannian manifold with a dimension that's larger than or equal to 2. And we have a map of this manifold that is a CR diffeomorphism, where R is some integer larger than 1, which is uniformly hyperbolic. So this means that for each x on this manifold, we have a stable cone and an unstable cone in the tangent space. And the unstable cone is what Carlangelo mentioned in his talk. So this is a cone in the tangent space. So this lives in the tangent space of X. And we also have a unstable cone in the tangent space of Tx. And so this is in the tangent space of Tx. And the derivative of the map T maps this cone strictly inside that cone. So the image of this cone is going to be strictly inside. And for the stable cone, I have the same story, except for the derivative of the inverse. So here I have my stable cone in the tangent space of X. And here's a stable cone in the tangent space of the preimage of X, and the derivative of the inverse maps this cone strictly inside that cone. And now there's an uniform rate, uniform in X, at which these cones get contracted inside these other cones, and that's what makes the system uniformly hyperbolic. So more or less, this is what an Anosov diffeomorphism is. And as a second point, I want to explain what a globally coupled map is. So the simplest coupled map is just a product system. So imagine just the n-fold product of a map like this with itself. So this is a diffeomorphism of the product manifold. And you can think of this as a coupled system with n independent units. So each coordinate evolves according to t, and there is really no interaction between coordinates. But of course, this is not very interesting. So we want to define some kind of interaction. So we take yes. Yes, I'm going to write this. So this is the uncoupled system. And now, if we want to define a coupled system that's actually coupled, then we need a coupling map. I'm going to be a little vague here. So this is just some diffeomorphism of the product manifold. So this is the n-fold product of the manifold with itself, which is epsilon close to the identity. In some sense, this is going to be made more substantial later on, but for now, this is enough. So the way you should think of this is that if epsilon equals to 0, then this is just the identity. So you don't have any coupling. And if epsilon is small, then we barely have any coupling. So the coupled map is just going to be the composition of these two maps. In which order, it doesn't really matter, but I usually take this order. So I first do the coupling and then apply the uncoupled map. So this is the coupling map. And this is the coupled map. So this gives me a dynamical system on the product manifold. I can represent the state of this system with a vector, for example. This is the most natural way to represent it. But equivalently, I can represent it with the so-called empirical measure. I get this by putting a point mass on all the xi's and computing an average. So this is what they call the empirical measure. And maybe I'm going to use the notation UN for this. Okay, so now I'm going to get a little more concrete with the coupling. I want to look at coupling maps of a specific form. So we are going to assume that the coupling map is a function of at the ith coordinate, and this empirical measure mu n. So this means if I want to compute what happens to the ith coordinate, I only need to know what the ith coordinate is and what the average state of the system is. And this is what people call mean field coupling. And now if this F epsilon map has some nice analytical properties, then it holds that if these empirical measures converge weakly to some measure mu, then this map converges to F epsilon of mu. And in this case, we can understand this here as the coupling map for a system where the system state is represented by this measure mu. So now this is no longer an empirical measure. So this is no longer a system of finitely many coupled maps, but something more general. The way I like to think about this is that this is a coupled map system with infinitely many sites, and the state of these sites are represented by this measure mu, which is a measure on M, right? And this is the system I actually want to study, a system where I am not coupling finitely many sites, but infinitely many of them. And now I want to define dynamics in some way, because here I represent the system state with a measure. So to define dynamics, I have to define dynamics on measures. And how do I do that? So let's just go back to the case when we have finitely many sites. So I have mu n here, which is the average of these point masses on xi. And where does this go to if I apply this map to this vector? This goes to the average of Dirac masses supported on the T epsilon n image of X. So how can I write this differently? I can write this as mapping the measure mu n to the push forward of mu n by this map. Which was the composition of Tn and phi epsilon n, right? And this is something we can generalize to the case when we are not working with these empirical measures, but some more general measures. So in this limit, we are going to map mu to T composed with phi epsilon of mu, which is the coupling map that's associated to this infinite system, and we push mu forward by this map. And this is what people call a self-consistent evolution. And by self-consistent, we only mean that the map by which we are pushing forward mu contains mu. So this is all what self-consistent means in our sense. Now, this is something I didn't come up with. People have studied this before, and I first saw this in a paper of Keller in 2000. He studied a special coupling that was of the form identity plus epsilon times some function. This is a gamma, but it doesn't really matter, just some function of x. And now this is the point that this coupling term by which we perturb the identity only depends on mu via a parameter that we compute from mu. More concretely, I think he took the integral of some kind of smooth enough test function with respect to mu. So he was looking at this special coupling in the 1D setting. So he wasn't looking at Anosov diffeomorphism, he was just looking at circle maps which were uniformly expanding. And then we generalized this a little bit. This paper had a lot of authors in 2018 to a coupling where this perturbation term is of convolution type. We were interested in a specific kernel here, not very important right now. What was it? And this was still in the 1D uniformly expanding setting. And a little bit later with Matteo Tanzi, we looked at something even more general, where we take a function here that doesn't depend on the difference of y and x, but in some more general way. So again, very similar, except a little bit more general. And last but not least, Stefano Galatolo has a very recent paper about this business. I think it was published this year, where he looks at, well, on the one hand, an abstract framework, and presents a lot of applications, but they are also restricted to this case, to the one-dimensional uniformly expanding case, if I remember correctly. Yes, but also in 1D, right? Yes. And what are the results about? So these are the systems that people looked at, but the results are about fixed points of this self-consistent evolution, because in some sense that represents an equilibrium state of this system, this coupled map system. So what these results show is the existence and uniqueness of a fixed point of this self-consistent evolution, dynamical stability. So if we start from a mu that's sufficiently close to the fixed point, we are going to converge to it by this self-consistent evolution. And also statistical stability, so that if I change epsilon a little bit around, then the fixed points of these self-consistent evolutions are going to be close. And if we take this a step further, we can talk about linear response. So if the fixed point of this self-consistent evolution is a C1, sorry, is a C1 function of the coupling parameter, then we say that we have a linear response in this coupled map system. So that's what we did with Matteo Tanzi in that 2021 paper. Okay, so but what I wanted to emphasize is that all of these results are practically in the one-dimensional setting. So we don't really have anything in higher dimensions. And that's what this work is aiming at, to do something for coupled maps that where the units are higher dimensional and not uniformly expanding, but Anosov diffeomorphisms where we have locally these contracting and expanding directions. Okay, so in order to present the results, I have to digress a little bit and talk about our functional analytic toolbox. So first of all, I will talk about Banach spaces. These Banach spaces were introduced by Bassoon and Carlangelo Liverani in a 2021 paper. And so what I'm going to do now is introduce, well, a sequence of weak spaces and a sequence of strong spaces. And the weak spaces are in some sense like L1, and the strong spaces are, well, in some sense like BV. So what are these spaces? Let's take a C1 function on the manifold and some Q integer or 0. And we define the 0Q norm of H as the supremum of the integral of H against some test function, where the supremum goes for pairs of foliations of the whole space M and test functions that are in some good set. So here, L is a parameter that controls the regularity of this foliation, W, which is a foliation by stable curves. Q controls Q gives the smoothness of this observable phi and the stable direction. And this one here just says that phi is a C-valued function. So it's the power of C for the target space of phi. I don't want to get any more specific with this. I hope it's enough for you at this point. And we define our space as the closure of C1 for this norm. And this is going to be our sequence of weak spaces. Now, constructing the strong spaces is a little bit more difficult. So again, we take a C1 function and some Q. And we define the 1Q star norm as the supremum of H integrated against the divergence of phi, where the supremum again goes for a pair of stable foliation and observable that is in some good set. Oh, and here we have a D. So phi is a CD valued observable. And we then define the 1Q minus norm as some positive constant A times this star norm plus the weak norm. And we are still not completely ready. We still have to define what actually the 1Q norm is. And we define this by taking the liminf of the 1Q minus norm of G's that are epsilon close to H in the 0Q norm. So this is a bit complicated, but we have to do this because if we would just close C1 with respect to this norm, we would get something like that's more similar to the Sobolev space W11. And with this construction, we get something that is similar to the BV space. So what does this mean? As a remark, I would like to point out that if we don't have a stable direction, so the stable dimension is 0, so the map is expanding, then this weak space really simplifies to L1, and the strong space, where did I write the, oh yes, I didn't actually define yet what the strong space is. So let me just go back here. So we define the strong space, the B1Q, as the subset of the weak space where this norm is finite. Okay. Yeah. And so in this case, the strong space is PV. Okay, so this is all good so far, but it's not going to be enough for what we want to do. So we have to define another sequence of Banach spaces that's not in that paper. It's just in this paper, what I'm talking about right now. So what are our super strong spaces? So weak spaces, strong spaces, super strong spaces. These are going to be defined very similarly, except they will contain the partial derivatives of H. So here we are going to have the partial derivatives of H integrated against the divergence of a test function. And that I think we summed for all the partial derivatives. And the supremum again goes for pairs of stable foliations and observables in some nice class. Okay, so now we have our Banach spaces, And then I don't want to write this self-consistent evolution all the time. What I have written here, I want to write this with the help of a transfer operator. So now I want to define a transfer operator on these Banach spaces. And I want to work with that in what follows. So I can define the transfer operator acting on any of these spaces by the following formula. I think this has already appeared in some of the talks. So I hope you are familiar with it. Yes, I can do this because these Banach spaces can be embedded into the dual of this space. This is not trivial, but it is true. So I can do this for the map T, but what I actually want to define is not this, but the so-called self-consistent transfer operator. Which is going to describe the self-consistent evolution. So in this case, I want to apply the transfer operator associated to T epsilon mu to mu. And I will denote this as L epsilon mu. And this is what I call the self-consistent transfer operator. Now, to understand better how does this transfer operator act when I iterate it, let's try to write out. Yeah, I changed the notation a little bit, but maybe I can write H instead of mu to be less confusing. Let's write H here. So how does this look like? First, I have H, and then I apply the transfer operator of T epsilon H to H. And then if I call H1 L T epsilon H of H, then what I have to apply now is the transfer operator associated to T epsilon H1, and so on. Okay, I just do this in every step. I define H2 as the transfer operator associated to the map T epsilon H1, and so on. So you can see what happens is that I apply a sequence of transfer operators, which are very, very similar if epsilon is small. The advantage of writing it this way is that now I can see that I am applying and linear operators one after another, because when I write it this way, this L epsilon is a nonlinear operator, so it's not very nice. But if I actually write out what's happening, I can see that I am applying n linear operators that are pretty close to the transfer operator of T if epsilon is small. Okay, so I think we have all that we need to be able to talk about the results in a proper way. Okay, but I realized we first need one last thing, some assumptions about the coupling, because I left it off with saying that it needs to be epsilon close to the identity, and I didn't say anything more. But now that we have all our Banach spaces, we can actually formalize what we mean. So what are our assumptions on the coupling? We have two assumptions. First, we assume that for any H1 and H2 that are in the weak space and are also probability measures, the CR distance of the coupling map associated to H1 and the map associated to H2 is smaller than some constant times epsilon times the distance of H1 and H2 in our weak norm. So this is what we assume about how the coupling changes if we change the state of the system. And our second assumption is about how the coupling map changes if we change epsilon. So here we assume same thing, except now I am going to change epsilon to some epsilon prime, and H stays fixed. So this is smaller than some constant times the difference of epsilon and epsilon prime. So this is what we assume about the coupling. And what are we looking for now? We are looking for an invariant state or invariant measure, which is a fixed point of the self-consistent transfer operator. And we are also looking for an invariant measure that's actually interesting. So it's a physical measure. This means that if I take some H from the space of probability measures and I iterate it by the self-consistent transfer operator, then this sequence is going to converge to H epsilon. Then I call H epsilon a physical measure. So I don't think this is exactly the definition that Caroline gave, but it's more or less the same. So so these are the interesting invariant measures, and our first theorem says that if epsilon is sufficiently small, So this is how all of the results are going to go. If epsilon is sufficiently small, then something holds. So for epsilon smaller than some epsilon 0, we have a unique physical measure. Now, to go a little bit further, I still have to introduce some objects. So consider this set BK. So this is going to consist of yes, C1 functions that are positive and have integral 1. So they are probability densities, and their 1 Q+1 norm is smaller than K. And now we want to close this set in the weak norm. So this is going to be the closure in the 0 Q+2 norm. And then the next proposition says that if epsilon is sufficiently small, then there is an iterate of the self-consistent transfer operator that's going to leave this ball invariant. So from now on, let me just write for epsilon small enough. Okay, so this doesn't look too bad. If this capital N was actually just 1, this would mean that we have a compact set, and it is invariant. So if we also knew that the self-consistent transfer operator is continuous on it, which we can also prove, then we would have that we have a fixed point in the set. But and this is actually what we can get quite easily for circle maps. But in this case, we don't quite get it, just working with these two spaces. So the weak space and the strong space, we only get this for some iterate. So this is not saying a whole lot, but we need this to prove our main result. But for that, we need another set, which we call B K1, K2. So this is going to be a subset of B K1, for which the 2Q norm is smaller than K2. Right, and we are going to close this set too with respect to the 1 Q+1 norm. And now this set is going to be very good for us because it is going to be invariant under the self-consistent transfer operator, and the self-consistent transfer operator actually going to be a contraction on it. So we get a unique fixed point and exponential convergence to this unique fixed point. Let me just write this as our second theorem. So for sufficiently small epsilon, we have K2. It has to be bigger than 1. Such that L epsilon has, so the self-consistent transfer operator has a unique fixed point H epsilon in this set. And for each H, starting from this set, we are going to converge to this element H epsilon in the 1Q plus norm. Exponentially fast. And furthermore, we have statistical stability in the sense that if I take an epsilon and an epsilon prime that are sufficiently small, so below this bound that I was referring to here, then if I denote the fixed point of the epsilon self-consistent transfer operator as H epsilon, and the same with epsilon prime, then this H epsilon and H epsilon prime is going to be close in the 1Q plus 1 norm. Yes, so this is the main theorem as far as we got. And if somebody wants to push this further, it might be possible to get linear response, because this statement here shows some kind of Lipschitz continuity of H epsilon as a function of epsilon. But I think this can be pushed further probably to C1. Yes, I think I finished a little bit early, but this is all I wanted to say. Yes. Yes.
That your system is very close to H0, to the one which is completely uncoupled, or not?
Yes. Yes, it implies that in particular.
So the density which you construct is basically the density of the uncoupled system plus some small perturbation, more or less, right?
Yes. Yes.
Okay.
In this sense.
In this sense, all right, all right. So is there any hope to have a stronger kind of coupling and recovers kind of some parts of this result?
Can you repeat that? I didn't understand.
So,
what do you mean stronger kind of coupling? Oh, you mean in larger epsilon? Yeah. Yes, that's a very good question, because I thought about this a lot when I was looking at circle maps, coupled circle maps, because in that case I really believed that for that this is the picture what we see for epsilon small enough, when all of the maps that I am applying are uniformly expanding. But when you lose uniform expansion, you can somehow construct an initial density that's going to converge to a delta measure. So if I push the coupling to be too strong, then I can have this really strong synchronization. And I really believed that for circle maps, this is the only two possible behaviors, but I wasn't able to prove it even for the doubling map.
Why do you think that is not two values?
Because I tried constructing examples for a long time and I didn't manage. So that's why I believe that it's impossible for some reason. But if somebody can construct an example like that, I would be very interested. I was even trying to construct an example for couple doubling maps, where you can have convergence to like an average of delta measures. So not just to a delta measure, but an average of them. And I never managed to find an example like that. I thought that if I take an initial density that looks something like this, it could converge to like an average of delta measures, but it didn't. So I really believe that when I couple doubling maps, then either we converge to a delta measure or to the uniform density. And I don't see why in other settings we could have, well, similar, qualitatively similar settings, we would have something different.
In that case, what kind of couplings
Yes,
you had in mind? Because you making
diffusive coupling. So this so for the doubling maps, it's this kind of coupling. The convolution type. Do you see it? Or
okay.
Yes.
So because in general, very general coupling, they can do everything they want, so you can try probably find other things.
Mm-hmm.
But I had another question.
Yes.
In the convergence to equilibrium estimate,
yes,
the constant, let's say the C and the other constant that tells you the exponent of the exponential convergence.
Yeah, this is a gamma.
They will depend on epsilon, probably. This one.
Yes, I think so. So for sufficiently small epsilon, I mean epsilon smaller than some epsilon bar, and they depend on epsilon bar.
Okay, but how they also depend on H?
They don't depend on H. They depend on this set. So the parameters of this set, K1 and K2.
Once you choose the ball, they
yes,
then the ball, this is uniform. Okay.
Yes. So the way I see this, there's this epsilon prime that gives the limit to what I can do. And if I choose an epsilon that's smaller than epsilon prime, then I can choose a ball. And once I have a ball, I have these two constants.
So in some sense, it's a local contraction.
Yes.
It could be that if you choose H very far, you don't have the convergence. Yes.
Let me see. But there's that first result about the unique physical measure. So if I take H from anywhere from the space of probability measures, it's going to converge to the physical measure, right? So we cannot have, but it might not be exponential, right? Yeah, but the speed might not be exponential. That's right.
Thank you. That was my question.
So we are starting again with our last talk of today's session. We have Alexey Korepanov, who is going to talk about loss of memory in non-stationary and mean field coupled intermittent dynamical systems.
Thanks a lot. Thanks for having me here. It's absolutely great so far. I have an illustration for my talk. I hope you remember what it is. It's from Caroline. These are uniformly hyperbolic things, and these are non-uniformly hyperbolic things. And I'll talk about non-uniform hyperbolicity, or rather expansion. And to balance things out, I'll talk about something which is in here, maybe just a single point. I'll talk about two projects brought to me by different people, which both are quite elementary, but both seemed quite important to investigate. The first one is a joint work with Juho Leppänen. We looked at a variation of the Liverani-Sassova-Yanti maps T gamma, which take x to x times 1 plus x to the gamma mod 1. You can have many different formulations of this. This is one of the formulas, which is good enough for me today. And gamma is a parameter. So it's an interval map 0, 1 to 0, 1. Gamma is a parameter between 0 and 1. So we are in the finite measure regime. Take a sequence of parameters, gamma 1, gamma 2, and so on, and the corresponding maps T1, T2. And let's bound these parameters by some gamma star, which is less than 1. And I look at compositions of these maps. So let's denote T1n to be T1 applied T2 and so on applied Tn. And then I'll also need a transfer operator with respect to the most natural measure, in this case, Lebesgue. So I'll have transfer operators Lk given by integral of u v composed with tk is Lk u v dm for as usual u in L1 and v in L infinity. And I'll also denote L1n the composition of L's. So Ln composed with L1. So this is the thing. This is the non-stationary transfer operators. And I'll talk about memory loss. So I need some sort of functions, the class of functions to which I can apply this. Let's say H gamma is the class of continuous probability densities. So from 0, 1 to 0 infinity, so that the integral is equal to 1. And I'll also want that h of x doesn't blow up too strong near 0. And the derivative is sufficiently regular. H prime of x is at most 10x to minus gamma minus 1. Like if you expect that your function is behaves like x2 minus gamma, then the derivative is by 1 worse usually. And 10 is just a constant. Think of it as a large constant. You can in principle say what it can be at least, and it can be arbitrarily large. So that's a class of functions, and our theorem is that if you have two functions from H gamma star, so gamma star is my bound on the parameters, so that's the worst kind of measures I work with, then the transfer operators L and 1 applied to F and G converge in L1 at a rate some large constant, which whatever, times n to minus 1 over gamma star plus 1. And if F and G belong to H0, now H0 is, well, your function will have to be bounded. Then the same thing decays at most as large constant times n to minus 1 over gamma star. That is faster. That's the result. We know that these rates hold for stationary sequences of intermittent maps. And we know that they're optimal. This is Güzel in 2003, maybe. We also know that these kind of results hold and are optimal for Markov chains, which look like intermediate maps. This is work of Pitman and Lidval in 70s and 80s. And we have shown this for non-stationary dynamics. Juho needed this for his own applications to show the CLT, which has been shown in other ways by other people ahead of us. But what we managed to get from here, which was actually new and interesting, was the moment bounds. Moment bounds for observables which are Lipschitz in coordinates. So things like maxima or Birkhoff sums. I want these two results for what I'm going to talk next. And because I have plenty of time, I'll actually give you the proof of this. I thought you still regained too much energy from today, so I'll try to bore you to death. I'll give you the proof in the framework of Pitman and Lindvall. They worked with Markov chains. It's a particularly simple situation, and I'll give you the proof for stationary Markov chains. But then it will be the kind of proof out of many different proofs which can be done for this model, which can be generalized to my model. The Markov chain of Pitman is the basic renewal object So these are transitions and transition probabilities. And so on. And we start with, so this is a Markov chain, x0, xn, and the initial point x0 will be distributed according to some measure. And for this measure, we'll only know that it is concentrated sufficiently close to 0. these probabilities their tails should behave like at most like n to 1 minus 1 over gamma star for this model to correspond roughly to the intermittent map. So things which we do is like this. First, we observe that probability that x1 bigger or equal than k is given that, say, xn plus 1, given that xn is 0, is at most n to minus 1 over gamma star. It's just an observation. I'm stating the same thing again. Then the probability that you are at 0, xn plus k equals to 0, given that xn equals to 0, is always positive. Is always at least some small constant, which doesn't depend on n or k. This is the basic recurrence. You need it to be mixing. And when you work in a non-stationary case, you need it to be mixing in some kind of uniform way. You do that, then you start getting careful. You look at the probability that xn plus 1 is non-zero, and so on, and xn plus k are non-zero, the probability that you didn't hit 0 for k steps, given that you did see 0 some L steps ago. This, you can show this is bounded by the sum of over j of k plus j to minus 1 over gamma star. You start getting careful bounds. You can always bound this sum uniformly in L by k to minus 1 over gamma star plus 1, but that would be too rough, and you won't be able to get to the fast rate from here. Yeah, so you have seen 0 not so far in the past, and you ask what is the chance that you won't have 0 for k steps. This is, yeah, what is the chance that you don't see 0 for k steps, given that you have seen 0 in the past. So this is a quantification of how frequently you return to 0, and that if you have returned to 0, then with some probability, you will be at 0 for all subsequent steps. You exploit this to construct a yeah. It looks like, exactly. It's just that you need to be careful, but basically, yes. Then, using that you know how things return to 0, you construct a stopping time. Time tau such that x tau is 0, so you only stop at 0. And the probability of tau bigger or equal than k is asymptotically n to some k to some power beta, where where beta only depends on the tails of mu, but otherwise is independent on mu. So given two different measures, you can construct. No, not quite that. So this is fine, but what you want to say that these things are independent of mu. So regardless which measure you feed me, given that it's not concentrated too far to infinity, I'll give you a stopping time so that the probability to stop at time k will be independent of the measure. So let me write it like this. So just these things is independent of mu. Given that the initial state is not too far in the infinity, that is that probability that x 0 bigger or equal than k is less or equal than, well, let's say k to minus 1 over gamma star. So if you only know this about your measure, you can construct the stopping time so that these things don't care about the measure. And then given two different measures, you know that they each allow such a stopping time. And it means that you can couple portions of them at time k. And from there, you do the analysis and you get profit. So that's basically the proof. It should be enough to hypothetically reconstruct it. But this project, it seemed to me very easy in the beginning, but it turned out to be insanely delicate. Yeah, no, you couple exactly at 0. In the map, you couple when you get away from 0, when you get to the second branch. Yeah. This is in a way proof similar to the proof of Ly-Young 98, 99, 98, 99, yeah. It's also similar to the proof of Pitman. It's similar to the proof of Lindvall, even though all three proofs are different. And this is different yet. We had to choose one which would work in our situation, and we had to adapt it again. So that's, and the main part of this paper is probably moment bounds. But I only will need decay of correlations memory loss right now. The second part of my talk is work with Weil-Boxon. It's the opposite. It seemed a complicated project in the beginning, but it turned out to be quite straightforward. We look at mean field coupled systems. And it's absolutely amazing that I talk after Fanni, who introduced the motivation. So I can afford to be very specific. Let's say I modify my example of intermittent maps in the following way. I fix gamma and I let th epsilon h map x into x times 1 plus x to gamma plus plus something, say epsilon x squared 1 minus x integral of h of y e to x plus y dy. It's something which changes smoothly, which is smooth and changes smoothly when h changes in L1. And also at 0, it's about x squared. So it doesn't destroy the intermittent character of the map. And at 1, it's 0, so it doesn't destroy the Markov structure. But I don't want to state assumptions. I'll just give you the subject, this aspect. We have that, and then so H will be the global state of the infinitely many coupled maps, and this will be the evolution of one of the maps in this family. The space of functions, the space of H on which I'll work with will be, say, dr. This will be, again, positive and continuous functions on 0, 1. Which will satisfy condition on derivatives. The Lth derivative of x divided by of h divided by h of x will be at most some constant which depend on L divided by x to the L. For L less than R, so R is my regularity. It's the same as R plus 1 in talks by Fanni or Carlangelo. I'll want this. So 10 to the L is again some increasing sequence, which increases sufficiently fast with L. The actual statement will be that there exists this increasing sequence of constants, and these are actually very much computable for this example. And I'll want a condition. I want to put R here as well, but I want this set to stay compact in a sense. So the last condition I'll replace with Lipschitz of h r minus first derivative, Lipschitz constant at h divided by h of x is at most 10 to the r divided by x to the r. I hope it makes sense that conditions like this are reasonable. The invariant densities in intermittent family, they look like x to minus 1 over gamma. And again, as you take derivatives of this, you'll get additional negative powers of x over here. And we work with functions which also gain additional 1 over x each time you take a derivative. I'll also define dr1 to be those functions in dr which have integral 1, sorry, probability densities, and which have good enough tails. So integral from 0 to x of h of s ds is at most some constant, sufficiently large constant, times x to minus gamma, like that. The theorem is, so this is myself, and while is that, do I have parts of this? Is that both dr and dr1 are invariant under the object which I didn't introduce, under the self-consistent transfer operator. So self-consistent it's something which takes say f to L epsilon f as in Fanni stock, and L epsilon f is a transfer operator which corresponds to T epsilon f and the Lebesgue measure. So it's just that. So the theorem is that L epsilon, let's say dr1 are invariant under L epsilon, and there exists a unique fixed point in dr1. That's one thing, and the second thing is that for every h in dr1, we have convergence of L epsilon to the n h to h epsilon. And the convergence, we can quantify it in L1 by some constant times n to minus 1 over gamma star plus 1. And right, I will need R to be at least 2. So I'll want my map to be 3 times differentiable for this. For some time, I thought that I made an original discovery about the cones which intermittent maps preserve, these dr and dr1. But then I found something pretty much like this, only with r equal to 1 on one of the last pages in the LSV paper. So here goes my attempt at originality. but still, so what we have from here as a particular result for a fixed system for when you don't have the perturbation by epsilon is that the invariant density is in dr for every r. So the invariant density for the LSE map is actually C infinity. This is the third proof of this result I know, but it can become the first one published. The other two by Caroline. Caroline knows it's analytic. She has a neat argument for this, but it will probably take ages to write it down. I'm not saying it's difficult. I'm just saying that it will take ages. And there is another argument by Damien Thamin, which is using very clever, different ways to induce things so that you don't lose information about continuity of the regional map. But for us, this is, well, my proof of invariance of these cones is a direct verification towards. So and again, I have half an hour. So let's do the proof. The proof goes like this. Let's take f and g in dr1 and denote by fk L epsilon to the k of f, and similar for gk. Gk is L epsilon k of g. And write down what L epsilon to the kf minus L epsilon to the k g is. And I'll do it in the same way as is done in the paper Fanni was talking about, paper by Weil, Carlangelo, and Fanni. This is just an identity. This is L epsilon f n minus 1 dot 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 L epsilon f0 f minus same thing with f's for g. So L epsilon f minus 1 L epsilon f0 g. Plus a sum over j from 0 to n minus 1 over of L epsilon f n minus 1 to L epsilon f j plus 1 times L epsilon. I promise it's the only complicated thing, the only hard expression I'll mention I'll ever have. So L epsilon fj minus L epsilon gj times L epsilon g j minus 1 dot 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 L epsilon g0 applied to g. A strange thing, but it's just an identity. And if you ever worked with linear response, then you probably have seen these things many times. This is an exercise in triangle inequality, essentially. You try to group things together which you can compare. And then I have two objects here I'll try to bound. First is this. Now I'm in the setup of the sequential dynamics as we did it with Juho. I have a sequence of maps, epsilon f0, epsilon f1, and so on. And I apply the sequence to two different densities. And it pretty much falls in our framework there. And the rate here is n to 1 minus 1 over gamma plus 1. The next object is terms in the series. This bit with j's will be just something in h gamma. or in D R1 from the invariance. Then I take a function in the cone and I apply to it difference of two maps. And this difference will, it was an assumption in Fanni's talk. In my case, I have it very much explicit. So epsilon L epsilon F minus L epsilon G cool, but I don't have to work a lot because here's my formula, right? And you see that you change epsilon in L1 slightly, that thing is smooth. So I cheat as much as I can, but of course we will have some assumptions in the paper. We actually have them. So this thing is, I want to write this as epsilon times times some constant theta times H0 minus H0, where theta is bounded by L1 difference between F and G, like this. And H0 was the bounded cone from my paper with Juho. So functions which are bounded and whose derivative of 0 blow up at most as X inverse. That's the part here where we have the faster decay. So then up to here, I'll have that epsilon times the L1 norm of Fj minus Gj times H0 minus H0. And I can take the constant out of the sum. And I know how these things contract differences of H0s. So that's so the whole term is something like epsilon Fj minus Gj L1 times n minus j to minus 1 over gamma star, like this. And then copying the argument from Fanni, Carlangelo, and Boyle's paper, you convert it into induction argument. If you assume inductively that Fj minus Gj is at most some constant times n to minus 1 over gamma star plus 1, then using this, you are able to build induction. You can show it for all j's, for all k's in this case. And interestingly, this is about it. I was quite afraid of this in the beginning. I was expecting complications like things we had with Juho, but then we just found the arguments which work. We spent some time trying to put it in exactly the right way because you have to, because otherwise things are still complicated. But that was it. And I still have 20 minutes. What kind of What level of truth do you want my response to be? On Caroline's level 4, no, probably even level 3, I can answer. So a bit more rigorous than that. I think that it will work, but it can, or it might or might not get messy. I don't know. Yeah. Randomly, oh no, I don't. I know that I can make gamma depend on. Well, it was because of you recently I understood why Lindvall's argument works, and it was delicate and quite complicated. I don't know. I have a good guess, but I don't have a proof, and I don't think it will be something which is easy to write down. Even though when written down, I guess it will be easy. I don't know.
Thanks. As a map on H, can you say anything about its, I suppose this is an extension of Fanny's linear response question. Can you say anything about its you know, like the regularity is a, like not necessarily like about the fixed point, but about it as a dynamical system on H? Like, is it like, how differentiable is it really? I guess it's the question. With respect to H. So like fresh A differentiable. I mean, you know. Yes. From a strong space to a weak space, or like
Well, it certainly continues in H.
Yeah.
We actually, to get a fixed point, we use that, well, the cone is invariant, it is convex, and the map is continuous. And this is how we get, yeah, but differentiability. So it will probably be Lipschitz.
Okay.
But then, well, H is a function in L1. So if you want to differentiate, you want to take Frechet derivatives in L1 and see how many you can take.
Into L1. Oh.
Well, here's the formula. No. If you remember how to take Frechet derivatives, differentiate. The annoying thing is that when you take the transfer operator, you have composition with the inverse.
Yeah.
And you need to differentiate that, and then it becomes an exercise in calculus. I mean it. It becomes an exercise in calculus. I wish I had taken calculus recently. Yeah, oh, that, yes. When you teach it, you don't practice that much solving complicated things many times over and over.